See, I didn't word it.
That's okay. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. الحضور الكرام، السلام عليكم ورحمة الله وبركاته، وأسعد الله صباحكم بكل خير. نجدد الترحيب بكم مرة أخرى في اليوم الثاني من فعاليات ورشة عمل مواصفات وعمليات تصنيع حديد التسليح التي تنظمها الهيئة خلال الفترة من 26 إلى 27 من شهر ذي القعدة لعام 1435 للهجرة، بمشاركة عدد من المختصين في هذا المجال من داخل المملكة وخارجها. ونود أن نهنئكم مسبقا باليوم الوطني للمملكة العربية السعودية، والذي يصادف غدا 23 من سبتمبر الأول من الميزان بمناسبة ذكرى 84 لليوم الوطني للمملكة العربية السعودية، متمنين لهذا البلد التقدم والرخاء بقيادة خادم الحرمين الشريفين حفظه الله وسمو ولي عهده الأمين. الإخوة الحضور، مقارنة العلامات التعريفية والنتوءات بين المواصفات الأمريكية ومواصفات الآيزو لحديد التسليح هو عنوان ورقة العمل السابعة لهذه الورشة، والذي سيقدمها الخبير الأمريكي روبرت جولدويسكي، فليتفضل مشكورا. It gives me a great pleasure to invite again His Excellency the U.S. expert, Mr. Robert Goldwisky, to give more presentations and more of his knowledge about this very particular topic. So please, Mr. Goldwisky.
Thank you. Thank you, and good morning, everybody. Can the interpreter hear me? We good? Okay. First of all, thank you for being here this morning and coming back. I hope you enjoyed what we did yesterday. It'll be a little different today. But what I still want to maintain and encourage even more is the interaction and questions coming from the floor, because I think that's important that we do that. We will try to follow to some extent the agenda here, although there will be some modifications perhaps as we go. I will talk to you as much as I can about the things that I know, so that's what we will focus on. There was some discussion yesterday, questions about, it was kind of related to the marking. I don't expect to go into marking requirements to any degree. I'm not an expert in them, and there's a complex series of all the different specifications and their marking requirements. So I did not attempt to try to sort that out to bring any clarification of that, except to say that obviously that is something you have to look at. If you want to meet any specific country specification, you have to follow their marking requirements, and each are different, so you must follow them. They're mechanical, not metallurgical, so hopefully straightforward. There was some questions about what I'll say is metric versus English, or inch-pound units versus SI units, depending on how you call it, particularly with respect to ASTM specifications. So that's what the purpose of this particular letter that you have up here is, to get to that subject. U.S. specifications, ASTM specifications, they're not U.S., they're ASTM. Had, of course, many years ago, had started down the path of trying to go to the SI units of measurement in all of their specifications. Hence, you have statement, they will be titled, for example, 615, 615M, M for metric. And there was also a push some 10 to 20 years ago to start marking, for example, rebar in metric units instead of, in millimeters instead of the inch-pound units, which are unique, go back to eighth of an inch increments. That's where those numbers come from. However, in the last few years, there's been a push to go back and to stop using the SI or metric units for bar identification in North America. And so what I'm showing you here is a resolution of the CRSI. And remember, CRSI, yesterday we discussed, is the Concrete Reinforcing Steel Institute. So it's basically a consortium of steel rebar producers who get together, who have this unified voice, if you will, CRSI, to help guide their way through the commercial and the specification body system, if you will. And they did publish this resolution that we will go through, which specifically recommends that all producers in North America go back to the old inch-pound system of identifying bar sizes. So we will read through this, what their logic was, and what their proposed plan of action is. So you need to be aware of this if you're dealing with the North American market. If you're concerned about what you're doing here, you can still maintain your system of bar identifications, which I presume is metric, and not too different than the alternative metric system that's in the ASTM spec. It's still not known whether they will plan on keeping that in there. I expect the answer is yes, but rather than combining them with dual units on every table and so on, you will have a separate table for metric, and you should order the rods one way, the bar, one way or the other, but not something you could expect to meet both. And I think that's the process that we'll read through, but we can read through this statement from CRSI, and then we'll go to, and I'll try to pull up A615 as an example, and we will discuss the impact of slight differences in the weight per unit length or actual cross-sectional area of bars, depending on whether they're identified as metric or SI units or inch-pound units. So we'll read through this, if you will, and try to get an understanding of the reasoning they used to come up with this, and then we'll discuss that after we're done. And this is a resolution of the CRSI Material Properties and Bar Producers Committee on the issue of reverting to inch-pound markings on steel reinforcing bars. Whereas, as a direct result of the Presidential Executive Order dated July 25, 1991, the Federal Highway Administration enacted a policy mandate for metrification administered through the State Departments of Transportation. In response, the Concrete Reinforcing Steel Institute encouraged its members to adopt a system of soft metric markings on reinforcing bars for all size and grade. And I emphasize here, soft marking. So which meant it didn't change the size of the bar. They just put a metric type mark on it, but it was still made to the inch pound requirements, not the metric requirements. That's I guess, their interpretation of soft marking. Okay, and then next statement. Whereas since the late 1990s, essentially all domestically produced reinforcing bars have been marked with soft metric labeling for size and grade. And whereas, as a result of this transition to soft metric bar markings, no intentional changes have been made to the physical properties of the reinforcing steel bars. Whereas the Federal Highway Administration no longer mandates metrification of federally funded road and bridge construction projects. In a memorandum dated 28th of November 2008 from Jeffrey Panit, Federal Highway Executive Director, states, given that all of our partners have abandoned metric measures, and I'm not sure what he's referring to there, we have concluded that continued mandatory use of metric measurements in the Federal Highway Administration's daily business activities is impractical. Accordingly, I am rescinding the prior guidance dated June 1, 2001 on this issue. The use of metric measurements is no longer mandatory in our daily business activities. Each office may use its own judgment on the value of metric measurements or dual units based on the audience for each document. For offices that wish to use dual units, we encourage a reversal of past practice by presenting them in the format of inch-pound value followed by metric value in parentheses. And whereas a result of the change in metrification mandate at the federal level, all state departments of transportation have now abandoned plans to adopt a metric measurement system. And as such state departments of transportation no longer require materials to be specified and sourced in metric size and quantities. Whereas the U.S. General Services Administration has indicated that switching the labeling to the actual bar sizes in inch pounds would not be an issue for GSA. And whereas the American Concrete Institute, through their Technical Activities Committee, has strongly encouraged CRSI members to mark reinforcing bars with traditional inch-pound size designations. ACI is the standards body within the United States responsible for developing the Concrete Building Code. The Concrete Building Code and other ACI documents reference the inch-pound size as the primary designation. Whereas the large majority of non-governmental construction community never adopted the metric measurements in their plans and specifications. And whereas the continued use of soft metric markings on reinforcing bars has been reported to generate confusion on job sites, as plan specifications prepared in the inch-pound standard and bars marked in soft metric require an additional level of understanding and interpretation so as to ascertain the correct utilization, placement, and inspection of reinforcing bars. And whereas there appears to be no logical reason to retain the soft metric bar marking system, it is now therefore it is resolved that the Concrete Reinforcing Steel Institute, Material Properties and Bar Producers Committee, number one, urges the Concrete Reinforcing Steel Institute Board of Directors through the Concrete Reinforcing Steel Institute Engineering Practice Committee to encourage CRSI producer members to revert to an inch-pound marking system for all sizes and grades of deformed reinforcing steel products. The intention of this resolution is for all new rollings of reinforcing steel products, no later than January 1st, 2014, to be marked with inch-pound markings. Providing a 25-month phase-in period should permit producer members sufficient time to retool finished roll inventory to the inch-pound marking system, as the rolls need to be replaced, significantly reducing or eliminating the need to unnecessarily cut new rolls with the sole intention of meeting the intent of the resolution. Number 3, as the ASTM specifications for reinforcing steel products permit reinforcing bars to be marked in either soft metric or inch-pound markings, existing inventory of soft metric bars can continue to be sold alongside inch-pound marked bars during and after the January 1st, 2014 phase-in target. The intention of this resolution is to reduce confusion and the chance of errors and delays in the construction supply chain. All of the CRSI members are strongly encouraged to revert to inch-pound marking system for steel reinforcing bars as soon as practical to minimize any additional confusion to the supply chain of steel reinforcing bars. Now, the best I can determine, this is all about the sizes of bars rolled in North America that are really dual-sized with the soft metric conversion. And so what we need to do is go to A615 specification. So this is 615-14. This is the latest one now available for download on the ASTM website. It has this table, and I can blow that up so we can see it, of deformed bar designation numbers, nominal weights, nominal dimensions, and deformation requirements. And you can see it has a bar designation number. The first one is the inch-pound units, which is really equivalent to a nominal eighths of an inch. It also has in brackets following the soft conversion to metric in millimeters. And those were the numbers that were put on, actually rolled into bars. That's what they're saying is no longer will we use that soft metric number to identify the bars. We only use the one on the left to go back to that system. The actual cross-sectional areas, nominal cross-sectional areas and requirements for sizes did not change. They stayed as this table identifies. Now, there was a question yesterday in this meeting about concerns about if you order it in English but you test it in metric, you can have a problem. And we will try to identify that. Because in 615, if you go to the end, there is an annex. And this is A1. A means an annex table. And this is alternate bar sizes. The following requirements shall apply only when specified in the purchase order or contract. When specified, then this following tables replace the table, particularly the table one we were just looking at. And so in this one, there is only the metric designation. But the important thing here is that the nominal cross-sectional area that you can see, and let's just take one as an example. Let's take the first one, 10 millimeter bar. the cross-sectional area, the nominal cross-sectional area of that 10 millimeter bar is 79 millimeters squared. Let's go back to the soft conversion of table 1 for a 10 millimeter bar, and there it's 71 millimeters squared. So this English bar, even though it said 10 millimeters, is a smaller bar than if you ordered a 10 millimeter metric bar. And of course, if you test it, and remember, you use in rebar, you use the nominal size, not the actual size in a tensile test. So if you test this bar and say it passed based on a nominal cross-sectional area of 71 millimeters, but if somebody buys it and says, well, you're supposed to meet this spec, he's going to divide that same load not by 71 millimeters squared, but 79 millimeters squared. And he's going to get a different number. And you may not pass. So you have to be very clear throughout the specifying and ordering process whether the bar is English or metric. Because you can get in, the soft conversion can get you in trouble. Yes?
But the size 3 in the edge system not equal 9.5.
Yes. Exactly. Yeah, and we call it 10 because we call it a soft conversion, which means not exact. So you call it a 10 because it's close to 10, but it is not 10. It's 9.5 or whatever. So yeah, that's why you can't, in other words, it can be ordered to one or the other, but the set of requirements for those then are totally separate. So you cannot order it or supply it, make it to one of table 1, and then expect somebody to certify it based on the alternate or annex table 1. Yeah. So in other words, if you need it, if you're ordering this product, A615, for your use here in Saudi, you should order to the annex table size, and then to the metric. The A1 table, not the number table 1. Yeah, that's per convention. You need to be there and say, I need 8 millimeter. You could probably get it put in, but you need to be there. Apparently, whoever was representing these people in that meeting said, we aren't making 8, so we're not going to put it in. And in North America, I don't know that necessarily anybody does. But obviously, there's no reason for it not to be there if there's a need for it. If somebody says, I have a need for 8 bar, goes to the ASTM committee, you can get it in. So they're pretty good about that. Yes. Yes.
تصمم على ان كروس سكشن الان مختلف 60000 لو اخذناه بس اذا انت حسبت الان كان واحد الفرصه اللي حققت هذه 420 عند السكشن هذا يمكن الفرصه تختلف الفرصه اللي تحقق عند على مساحه هذه قد تتغير. بس اذا كان يصح الفرص اللي تتفق 120 على نفس المساحتين على نفس المساحتين، هذا ما في مشكله، يمكن عندي ضغط. بس يمكن الدروس مقصودي تتغير الفرص.
لا ماشي الحال بس والله هذا حتى
I have a question over here.
السبيكر ما سمعك وذلك.
Yes.
وانا عارف قصدك بس ما في مشكله كلام مضبوط.
يعني all available are in metric. And when we specify rebar diameter 14, for example, or 16 millimeter, is that exact what is available or not? This is the important thing for us as designers.
Yeah. Yeah. But in that case, since you are becoming, Sasso is becoming active in ASTM, and you're coming there, that's something you could easily bring to ASTM and say, for our market, we need these sizes in this table, and we can put them in. We just know. We didn't use them, you are, but if you want to use that specification and you're a user, this is supposed to be an international spec, we will put it in.
Yeah.
So we just need to know. We need to know, you tell us, we need these sizes. It's just another line in this table. It's no problem, you know, to anybody. So that I think is a very doable thing. Don't let that keep you from considering this specification for your use, because that can be changed. And it's simply a matter, nobody has asked for it, so it's not in there. You need to ask.
Excuse me, my question is not answered.
Okay.
My question is not answered yet, because I want a specific answer. What is available in the market now when we purchase, or when we specify, and then the project owner purchase? They purchase based on the SI unit, millimeters, number 12 mm, 14, 16, and so on. Is that matching with our design or not? This is very important issue. I need, if somebody can help us to answer this, please.
Okay,
You want to do that?
well, for the market here, the numbers are long time ago, since UNESCO used to be the controlling factor, and we have number 6, 8, 10, 12, 14, 16, 18, 20, 25, 28, etc. So this is so far the standard, and that's what you have in SASO number 2. So in brief, SASO number 2 designation is the standard for Saudi Arabia. And I believe that's what's available also for the producers. They are producing these sizes available. Now, coming to the US decision in the CRSI, I agree totally, because it was meaningless, that soft conversion. It's useless, really.
Yeah.
I mean, we are following the education there and everything, so we know it has no meaning in real life, even for calculation
For
purposes.
you, it just made things worse. So
The Canadian, basically, they are using the metric system, and they have different designation, though they are using ASTM, but with different designation, which meaningful. For example, they have number 15, which means something. So they are, I understand there's no problem if we adopt ASTM, whatever, any number of these, that the table here can be, we can put our table in SASO number 2 instead of this table, with all the information we have, and I believe truly there is no problem. We have discussed this already with STM long time ago. There's no problem in having our table instead of this table, and things will be just fine. If there's any other modification anywhere referring to the sizes, we can include that.
Yeah.
Now, for the ACI, in that statement, I don't think it was that accurate, because ACI 318, it has SI units and it has what they call metric, and they have inch pound. And they produce both of them up to today. We are, in our building code, we are following ACI 318 in the concrete building code. And in that code, we have also modified it for the bar sizes to follow what we are using here. So we converted whatever numbers there, this magical soft conversion, we put our own, so we modified them accordingly. And now in our building code, we are already included, we are following STM in one hand in the building code, and we are following the bar sizes of SASO. So things are, I don't see any problem at all for anybody to be concerned about anything. Everything is fine. Thank you.
And now that even in this discussion, I get a clearer understanding myself of the impact of that statement. And actually, it's beneficial because the way it was with the soft conversion caused all the problems. So we need to separate the two because they are uniquely different, and they should stay that way. And again, as long as ASTM keeps a table of this sort, so you can order it to metric, and it's a hard metric, and you won't have the testing problems that we discussed earlier, because it will be clear. It will be marked one or the other, but not both, because you can't have it both ways and be accurate. Is your question answered? Okay, thank you. There we go. Yeah, we need to.
Hello. I'm from Hadid Al-Raji Steel, Muhammad Ibrahim. Actually related to this standard annexer, what you added in the last version in 2013. This table was not there before in 2012 drafting. Okay.
Okay.
In this connection, I already communicated to the ASTM related to as we are working in the matrix system, so there are confusion with the standard. And there is a comment we already sent to you to elaborate this table to add sizes like 14, 16, 18 mm and 22 mm. That will match the total requirement of the market and will be follow as SI matrix system, and conversion for the deformation and all other things will be available readily. So there will not be any confusion. And I received the email from you that you are going to consider in 2015 drafting. So I want to know there is any discussion on this, or it has to be done in the coming standard from ASTM 615 grade 60.
Okay. I'm not sure I understood the entire context of that question, but
I will repeat for you.
all right.
He raised a claim or a comment to ASTM directly regarding that bar designation. He asks them to consider sizes, the missing sizes here is 14 and 18 millimeter, as well as 22 millimeter. Not considered here. It's common here in the Saudi market. Also, he asks them to consider the deformation and all units to be metric system, not inch system in this table. But it's not considered in the new version. They confirmed, they replied to him we will consider in the new version of 2014. And now he saw the 2014 and the comments not considered in the table. Thank you.
Okay, you saw 2000. This one is, okay, didn't follow that last part, but you're saying that oh, okay. Thank you. I do not represent ASTM, no. I'm active there, and you know it's unfortunate that they didn't go with that. But typically, the reason maybe they didn't is they had no one there to. You can write them a letter, but to get real action, you have to be there, or you have to have a representative who is supporting your position. That's the way that system works pretty much. Yeah. And I think your request seems very logical. Sometimes only one location or even just one country may not get it to happen. You need to, one of the things you do, and I do this all the time, if I want to get a change, but I run into resistance, you have to get a number of people, what I call a critical mass of members who all want the same thing, and they can't ignore that. Then they have to act to it. And I think that's what we need here. I certainly have a lot of empathy for your position on the need to make ASTM as metric as possible, but I also agree that it's best to keep them separate. And so it's clearly one or the other, and that trying to blend them is what caused most of the problems we have seen. So to do the metric correctly, the reality is the people sitting in North America don't understand what your needs are because they're not using it. So we need your input, and we need a collective input as much as possible. So work with the other people who have the same problems and band together and submit your requests in unison, and you will get more attention. That's my opinion because, again, I don't represent ASTM, and no real individual does. It's a committee. And, yeah, there are people on the committee with more power than other people based on just experience and time spent. And that's something that somebody like I recognize. I know who has the power and who really doesn't. You need somebody like that to work with you to get this to happen. But I encourage you to keep trying. Don't give up just because your first attempt failed. Okay, it can be changed. I think if you send me the letter, I could then help you identify the right people to contact to make it happen.
Excuse me. I will, during the break time, I will show you the communication which I made to them, and I will hand over to copy of that to you also. So you can also push up with us to sort out all. This is a global problem actually. Yeah. The people in the market. Yes, so we recommend again to have a separate table, and one for each, one for SI, and include all the sizes as SASO have the sizes from 8 mm up to 40 mm. That will also be converted from inches to SI and will be displayed as an Excel or elaboration on this table itself. So it can sort out the problem and confusion. Thank you.
If ASTM, and I believe ASTM is certainly of the position, they want to serve, they want to provide what logically the consumers want. They are there to protect the consumers. If the consumers need these sizes that aren't in this table, they should consider putting it in. There is no logical reason for them to exclude that. Certainly, it doesn't matter what the North American producers think because they're not making this size. So they should not care one way or the other what's in that table. But if you are and the industry, the consumer wishes to have those sizes, wants to order them, they should be in the spec. That's my opinion. And I will help you direct that.
Okay, thank you.
Yeah, if I may, two things really. One, by the agreement we have here, SASU, with ASTM, we can put our table. So that shouldn't be a problem for us if we decide to, I mean, we can amend even this table or instead of this table, and we could have our SASO as it is if we choose so. The other point I would like to make, I like this table. I'll be honest with you. There is a reason for it. Having so close sizes make it difficult to distinguish them in construction. And that's the reason really why we don't have 14 here or 18. Because they are not easy in construction to distinguish these parts. So it's easier to, by spotting them, you know this is what it is. So that's, I mean, why the American making and the Canadian making distinction, it's to make it visually easier to see the part in construction. So it shouldn't be a problem either way. I mean, we could go either way, but I mean, there is a reason for this also. It's not something wrong here that I need to amend. No, it's not necessarily. We can discuss it, and if it's, we can go either way, yeah.
Yeah, and those kind of discussions need to go on among the people that have an interest, because there is typically, on one hand, well, that sounds logical, but there is a reason why you don't do that. You have those discussions in ASTM. And if there's, of course, a strong opinion against it, it will be difficult to get a change, because the way ASTM operates, it only takes one vote, one negative vote to stop the process. It can be overridden, but it's very difficult. And there has to be good reason to do that. But so it's all these things have to be considered, and maybe they have been. I don't know, because I have not been party to those discussions. I suspect there has been that kind of discussion. And the tolerance level, all those issues do come into play. Yes?
My name is Faisal Alidan. I'm from Rajah Steel also. I just want to elaborate about what my colleague Mohammed already said about communicating with ASTM. In 2013, we already communicated with ASTM, and they were very supportive in adding 4 grades for us, or 4 sizes, different sizes, as our request. The only remaining is what already my colleague Mohammed said about some elaboration about the inch and the metric and all of that. But frankly, in 2013, they were very supportive, and they updated by adding 4 grades because of our request. So I just want to elaborate on that. Thank you.
Thank you. All right. Where are we? Yes. Yeah.
Yes, you go to take the exact. So any discrepancy in the nominal to the exact,
Yes. If, yeah, you're saying the Sasso uses the exact diameter, that is the exact calculated diameter, because you take, you would actually on an individual test get a weight per unit length, then from that calculated an average diameter. But they use that of the test piece as opposed to the nominal diameter of that generic size. That's certainly different than ASTM, and can easily result in differences of results in terms of testing. So if it's to ASTM, it's nominal. If it's to Sasso, it's actual. That's the way it is. You just have to, depending on which ones it's ordered to. But you can't expect to blend those two together because there will be error.
The calculation of Sasso and this table are the same, so I don't know. There's no difference. This table here now, the diameter and the area exactly as it's in Sasso.
So you use nominal size.
Okay. This is the actual, supposedly the actual diameter, and the area here, I know them. They are the areas that we have it in Sasso also.
Yeah. You have that in Sasso as well?
Yeah.
Okay,
Same,
so that's not a problem. So, but
There's
if
no
you
difference.
do, if somebody does do that, that's not the way you do it. You must use the nominal size for the bar that you're bar size you're testing. And it has to be one of these on the table. And of course, as we said, you have to be clearly distinct whether you're talking this table, which is the metric table, or the other table, which is the English or inch-pound table, because they're different. There is no, the soft conversion does not work, and I think that's what we're saying. So I think we're pretty much concluded there. Yeah, anybody that's using actual size to calculate strength in a rebar test is probably, I don't know of a specification that goes that routing. If Sasso doesn't do it, I don't believe ISO does it, but truthfully, I haven't looked at a lot of specs for that particular aspect.
BS, I think. The BS takes the actual cross-section.
Do they? The BS takes the actual. That's what he was referring to as the BS spec. Okay. I don't know that. If it does, it's different and can result in confusion if people aren't aware of it.
But now the last edition of the ISO for the testing, he referred to use the nominal cross-section area. But in the last, he used the actual. And also the standard, he used the actual cross-section area. But now this is no problem because the weight it's positive. Then it's near the nominal cross-section area. But in the American, either he used the nominal cross-section area, and I think when we use the nominal cross-section area to calculate the tensile strength or yield strength, it's better because it is going to be some bar will be passes through the tensile strength and yield strength, but it does not passes in the weight because it transfers from diameter 11 to 10. This is not effect.
Yeah.
Effect. Then you will be. Then it's better to use the nominal cross-section area and calculate the tensile strength and yield strength.
Because at the end,
it's very important.
Yeah. At the end of the day, the bar is used in construction. The design of that product is assuming that the strength of each individual bar will be the design strength of the bar for a correct bar size. And so it's the total load capability of an individual bar that counts, and that translates to using nominal diameter, not actual. So it doesn't matter what the actual strength is, as long as each bar is capable of holding that minimum required load. that's the reason to use nominal versus actual. And of course, with rebar, there is no uniform cross-sectional area for stress determination anyway, so even that's another set of complications into the whole system. At the end of the day, you need assurance that a given bar for a given specified size has a minimum load carrying capability. Okay? Thank you. I don't have any, if anybody has any more questions on markings, brand, ribs, design, there's so many different kinds out there. I had no intention of getting into it. If there's something somebody wants to discuss, now might be the time to bring it up. About the only thing I remember is for the guys in the mill that were making this product, there's actually has been some wording. I didn't attempt to find it. But you can, in doing the bend test, you want to make sure you're not bending against those markings because they can cause additional stress risers that normally occur. That's kind of like giving you allowance for something that may cause a failure, but because you have to put it on there, it's still there. I'm not sure of all the logic. You actually have to be concerned about what's on the, how you align the test bar during the bend test to ensure that the markings themselves don't cause a failure. Mm-hmm.
This is what you're thinking about this
The mandrel diameter requirements are different. Yes. We discussed that yesterday, and there's there's variations in all the specifications of exactly what mandrel size you use for what bar diameter, and of course there's differences between the bend and the rebend diameters in some specs, but not others, and those sorts of things. That's the way it is. I don't.
Excuse me.
We ended up. Yes.
Sir, excuse me. Excuse me. Actually, in this table, the 32 mm, which is giving the maximum rib height, 32 mm maximum rib height. I already communicated to ASTM, Mr. Kevin. I think Mr. Kevin. There is a typing mistake in that. It is written 0.063, and in the metric it is written 1.6. Actually, this should be 1.06, not 1.6. So this point also we raised to ASTM and recommended to have amendment in that. And I have communication with Mr. Kevin for that also. You can see in the 32 mm maximum rib height, it is shown 1.6, 0.063 inches and 1.6. It should be 1.06 millimeter.
Okay. Yeah, I have to. So what you're saying, there's an error in this table?
Yes.
As
there
you
is
pointed out?
Yeah.
It certainly happens.
32 mm in average maximum average height for the rib.
So you need to write a letter to David Gustafson and saying, please change it.
I communicated. I have the communication. I will show you.
It didn't happen yet, huh? Okay. Too bad he's not here. I wouldn't know that, but obviously those things have to be changed. And again, if you're there and bring it up, it tends to get more attention.
Thank you.
Yeah.
Somebody's heat size may be 150 tons.
Yes.
For the billets to be rolled into rebars. Somebody else may go for 250 tons. Now, in that heat size, I mean, for the ASTM directive, you choose 2 or 3 samples to be tested per heat, but it does not. But it assumes that the 3 samples taken to be tested will be representative of the remaining mass of rebars. What if they are not? Because previously these the materials were hot roll product, where the chemistry was the guiding force for getting the properties. Now we go to the quenching system, basically most of them, for economic cases, where the water flow, the quenching speed, the pressure doesn't affect on the properties of the rebars.
I agree. And I don't know what to do about that one. Yes, a couple of tests on 150 or 200 tons of steel using the QST system, you cannot use testing to actually confirm the entire body because you can have local variations very easily. I don't know the answer to that one. Again, in North America, that's not a huge concern because there's not a lot of volume of that steel made. But in the rest of the world, for sure, that would be a concern. I think that probably, obviously, is a question that needs to be brought up and addressed. But I don't have the immediate answer to it. Certainly a real problem. All right. Going to switch gears a little bit now and talk about the steel manufacturing process. So for the steel makers in the group, this is going to be old hat and a little boring. But for those that haven't visited a steel mill very much, it might be somewhat interesting. But the idea here is I'll walk through the basics of mostly the kind of equipment and how steel is made by a couple of the various processes. We'll look at primary steel making, secondary steel making, steel casting, and bar and rod cooling. I should have said that's not complete there. Cooling processes after the rolling process. So we're going to look at the rolling process and the cooling process. So a steelmaking flow chart, we've discussed it a lot, but to go back and clarify, there's 2 primary options in steel production. The first is where it's an ore-based process and goes through either a direct reduction, which is fairly common here in Saudi, with the use of natural gas to reduce iron ore to direct reduced iron, DRI and HBI. Or you take that same iron ore using coal or carbon from coal as which is converted to coke, and limestone into a blast furnace and use that to reduce the iron ore, the oxidized iron, to metallic iron. In either route, you end up with reduced iron, which can go from a case of a DRI, will typically go to an electric arc furnace and it can be mixed that way, or the primary source, and is probably most typical for rebar, will be a scrap-based iron units that start the process in an electric furnace. For a BOF furnace, which is an alternative to the electric furnace, these two are the 2 primary converting vessels that convert the raw material to a nearly finished steel, hot metal steel. That is fed primarily by hot iron from a blast iron, a molten iron from a blast furnace. It is mixed with scrap to some degree in the basic oxygen furnace, but the primary purpose of the scrap mix in a BOF is for temperature control, because the melting of the scrap takes some of the heat out of the steel and prevents it from getting too hot and then reoxidizing too much. So you need to control the temperature of the molten steel, and the scrap iron helps do that. And then after melting, it goes to a ladle furnace, and then from a ladle furnace, where it may be just a metallurgical refining operation, or may actually have additional heating capability. From there, we'll go normally to a continuous caster and then cast into either slabs or blooms. Then that's a semi-finished product stage, which is then transferred to a reheat furnace, whether it's a billet or a slab, and then we'll go through a rolling process. Slabs go to flat rolled products, which can be plates, pipes, which can be made into pipes later, or it can be sheets that go into coils, which then are subsequently cold rolled and perhaps coated and whatever later as well. So all the flat roll processing comes out of slabs. Most of the what's called the long products, come out of billets. And these long products can be seamless tubular, it can be structural shapes of most any kind, or it can be bars and rods. And of course, rebar is all primarily down in this particular area. So the primary steel, if you divide these primary processes up into two categories, the electric furnace and the basic oxygen furnace. Open hearths are sometimes mentioned in specs, but if there's any left running in the world, I'm not aware of it. There was one up in Nizhny Tagil that I know of a few years back. I don't know for sure if it's running or anymore or not. But then we get an electric arc furnace. Let's look at that one first. The steel scrap is the primary iron source, with direct DRI and HBI, direct reduced iron, and pig iron can be used as low metallic residual supplements to a scrap-based system. Or you can run it on 100% DRI or pig iron as well. But it's just not, that depends on the region and where you're at and what the iron source availability and costs are. Electricity is the primary energy source, with supplemental energy coming from oxy-fuel burners or oxygen injection into a liquid bath, burning the carbon to provide energy, because you need energy to get the temperature molten, high enough to be so the steel is molten. And then refining or cleaning of the steel is accomplished using by oxygen blown into the liquid steel to remove those unwanted elements that are more easily oxidized than iron. So those things that burn off, and those things higher on the oxidation table than iron, will come out of the steel and go into the slag. That includes things like silicon and manganese, zinc, and many of those kinds of things. However, certain elements that are lower, and that's your primary metallic residuals, nickel, chrome, moly, and copper, do not come out of the steel, and they remain in the steel. Electric arc furnace is basically, schematically looks like this. It's made up of let's see, use this as a pointer as well, and I can look at it here. So you have your three carbon electrodes where the arc is actually generated between those electrodes and creates the heat, and it melts the scrap that's in the bottom of a relatively shallow hearth that has a very thick refractory for temperature control. The roof is typically removable so that you can add more scrap and raw materials into the furnace. It has a door on one end for inspection and perhaps sampling or oxy limits manipulation. And then it typically taps out of the other end. In this case, it shows a spout but most any electric furnace made today has what's called an eccentric bottom tap. That is a tap hole that starts at or below the actual level of the hot metal. The furnaces, the roof and side walls tend to be water cooled, prevent them from getting too hot. Another schematic of the electric furnace showing some more of the peripheries, the evacuation system to get the off gases out and to keep the atmosphere clean. So environmental issues have become very important in these processes. It also shows the eccentric bottom tap set up here where it's actually, you will have a refractory plug that you just blow out when you're ready to tap, and the steel will come out of there and go directly into the ladle. The advantage is the opening where the steel comes out is actually below the level of the slag that's in the steel. So it reduces the amount of slag you carry over into the ladle, which is beneficial for later refining of that steel. This is simply a vertical view showing these electrodes and their arrangement, triangular arrangement they will have in a furnace. Here's some actual pictures of some electric furnaces in operation, showing what they look like in actual service. You'll see AC electric furnace on here, and that's because for a while there was a tendency to go to direct current, DC furnaces. And the reason they went to DC furnaces is because the power that they were putting into these furnaces was going up and up, and they had serious control problems with alternating current at very high power inputs into these furnaces, and they couldn't control the surges of the electric power. And one of the solutions was to go to direct current. Direct current required electrodes in the bottom of the hearth itself, which became maintenance headaches. But then along came better electronic control, so now these power surges are no longer a problem for the high power AC furnaces. So pretty much they've gone back to all ACs. So the DC furnace had a short lifespan, and now it's out again. Yes. Mm-hmm. And so the control systems have made great strides for alternating currents, and now it's back to being the furnace of choice for electric furnaces. Another picture, front view of a fairly large furnace. You can see this part up here, which is really the big arm that holds the roof, and so it can actually pick up the roof and swing it away. And of course, the roof includes the electric graphite electrodes in there to get it out of the way. This is a process of scrap charging. This is called a scrap charge bucket here, and it's carrying scrap. It can also carry the DRI, although most DRI will have a automated continuous charging system as opposed to a single bucket charge. But scrap is almost always, well, there's always options. There are some systems that actually preheat the scrap and then have a conveyor system for charging scrap into the furnace. But this is probably most common. It's just a scrap bucket that's filled somewhere outside the building. They bring the bucket in and then charge it in the furnace. You can see the furnace roof is starting to lift already from this line of fire that you see around there, and it will swing out of the way, and then the bucket will come over the furnace. Here's the furnace here, and then clamshell open up, drop the scrap into the furnace. This shows the tapping side of the furnace, where the actual furnace frame will be tiltable. It's a huge, heavy-duty tilting platform to actually pour the steel out of the furnace into the ladle down here. And this is part of the process. The stream itself will not be as large as what you see here. Mostly that's just sparks and a little bit. The stream itself is much smaller as you're tapping. But this tapping process, typically, it may take, high-powered furnaces these days can go make a heat in as short time as a half an hour, 30 minutes. And it will take 2 to 3 to maybe 5 minutes to actually do the tapping to get the steel out into the ladle. Now, the basic oxygen furnace, of course, is doing the same thing. It's refining the steel, but in this case, their feed source is mostly liquid pig iron coming from the iron ore, from the blast furnace that we showed a picture of. And the burning of carbon from the coal and coke is the primary energy source to make the iron in the first place. But the iron is typically very high in carbon, maybe 6% carbon. And that has to be blown out with oxygen, hence that's the name basic oxygen furnace. And in the process of blowing that carbon down to the carbon level that you want for your steel, of course, is where the heat is generated. It keeps raising the temperature. This refining, it also, the blowing that oxygen in refines the steel, again, a similar way to what we did in the electric furnace, is you can remove all the elements that are higher in the oxidation scale by blowing oxygen into this liquid steel. So generically, a BOF furnace will look something like this. Interesting thing is the amount of steel in the furnace is a very small portion of the total volume, because all the rest of this is used to just contain the reaction process as you're blowing the oxygen in there. And the oxygen is blown down through the center lance into the steel. The many operations of a BOF vessel. One is there is a scrap bucket as well that they put some scrap in there. The science of mixing the right amount of scrap with the right amount of iron is kind of interesting. And there's, I know some people that have written computer programs to do that. You also charge the hot metal into the vessel. You can see it held at a slight angle when you're doing all this. And after you get it in, then you do the blow itself. With the oxygen lance. You may turn it down. This is called a turn down position to check and see. You get samples for determine the chemistry, that sort of thing. And eventually, after it's correct in temperature and composition, you will then tap it, which is, tilt it the other way, pour it out a tap hole into the ladle. And after you're done, of course, you try to stop this process as soon as you get some slag entering into this tap stream. You will stop it and then dump the slag out in a slagging process to be removed. And just used in whatever way you can use the slag and reclaim it. So that's the basic operations of an electric furnace and a BOF. There's a picture of a BOF shop where they're actually charging the hot iron from a ladle vessel. Typical differences between electric arc and the basic oxygen furnace. BOF steel will be lower in metallic residuals, and that's the copper, nickel, chrome, moly that I referred to later, because the primary source is iron ore, and iron ore doesn't necessarily have those metallic elements in it. BOF steel will have lower nitrogen levels. One of the characteristics that is of concern to us when we start talking about bending and rebending. But BOF, because of the high volume of CO generation from the carbon burning, and that's the process by which the nitrogen is removed from the steel. Other residual elements in the steel, phos, sulfur, and eventually the oxygen and hydrogen, and any alloy additions, will be dependent on specific practices after it's melted and not on the melting process itself. So those things tend to be independent of whether it's an EAF or a BOF iron source, steel source. EAF operations can equal essentially all the quality characteristics of BOF steel, and they have done so in many cases. That doesn't mean that all EAF furnace shops are capable, because they have to have the right equipment, the right operations. Many of them don't and struggle to match the quality levels. But just because it's electric furnace does not mean it can't do it. Because after all, once the steel is melted, it doesn't matter how it got to that point. It's how you treat it from that point onward. To me, one of the more critical products that certainly we tried to make electric furnace is tire cord. Extremely clean, extremely pure product, but it can be made on electric furnace and is routinely. 10 minutes? Yep. We'll take a break. Now we'll talk about secondary steelmaking processes, ladle metallurgy station, or a ladle arc furnace, or even a vacuum degasser. These are all processes that one does after the steel is tapped from the primary vessel to the ladle itself. This is what a ladle looks like, full of steel, ready to be processed in a, some steel mills don't even have any processing. Once it's tapped in the ladle, you add the alloys at that point during the tap, and then it's done. You take it to the caster. A rebar operation might well be this way, because so many of the operations done in the ladle metallurgy station or ladle arc furnace, or even the degasser, are not necessarily a requirement for rebar production. Unfortunately, the reality of the world is rebar is the most basic of the steel products in terms of requirements to be made. Hence, when you start up a steel mill, that may be the first product you make simply because it's the easiest one to do. A ladle metallurgy station is a location where the ladle of steel can be treated after being tapped from the primary melting vessel. It usually includes stirring capabilities like injected gas or electromagnetic stirring, alloy addition equipment, slag treatment facilities, etc. For these gas stirring capability, probably the most common is to use one or more refractory porous plugs at the bottom of the ladle and then inject the gas through that for stirring, for cleaning the steel, cleaning out inclusions and things like that. But there are alternatives like a lance, typically not as good and used only in emergency, or electromagnetic steel stirring, which you don't include a gas stir, which has its pluses and minuses and is used primarily in very specific and applications of steelmaking that are unique, not rebar. Although I know of one shop that has EMS, so you may choose to do that for various reasons. And of course, final trimming and alloy additions are done in the ladle. Carbon, silicon, manganese, vanadium, chrome, the kind of things you might use in a rebar production process. A lot of the original deoxidation product, the block as they call it, the silicon manganese or aluminum again not used much in rebar, can be added at tap, or they may be added at the ladle furnace. And there are pluses and minuses for both of those routings. For rebar, probably mostly done at tap, or at least the primary addition is done at tap if you have a ladle furnace, and then you just do the final trimming at the ladle furnace. Slag chemistry can be adjusted at this ladle metallurgy station, and of course that's not a lot of that is done with rebar, but that's where you get things like sulfur control. You can, or You can recover alloys that are added that may be trapped or reoxidized into the slag. The slag chemistry adjustment is typically adding those things that reduce the slag, and so that the metallic elements that may have been oxidized and go to the slag can revert back to the steel. And you can save the value of those alloys by getting it back into the steel itself. It's primarily for electric furnace operation. It's your primary source of desulfurization. Calcium added to the slag combines with the sulfur in the steel and removes the sulfur into the slag. The ladle arc furnace is really a ladle metallurgy station with the addition of some small arc electrodes, similar to an electric furnace, only not as large. And the purpose, of course, is to do the final adjustment of the temperature so that the temperature of the steel going to the caster is the correct temperature. So it's part of quality control. It's also very useful operationally because then you can hold the steel in the ladle for an extended period of time if there's an emergency at the caster, for example, and still maintain the correct temperature. Typically, it went very well with electric furnace operations, but you can have similar operations now with BOF steel shops. This is a ladle, some pictures of ladle arc furnace. It's really nothing more than the ladle itself brought over to a station, whether on a crane or on some rail system, and then a roof dropped down over the ladle. In both these cases, the roof shows a gap between the roof and the ladle itself because it makes more dramatic pictures with the sparks flying out. But reality is they drop the roof right on the ladle and you don't see these sparks flying. Another picture of that similar ladle furnace, again with a slight gap between the roof that you drop on it and the ladle itself. But these are wondrous things because I lived through the period where they didn't exist to where they did exist, and the quality of the steelmaking operation, steel, just dramatically improved. One of the used between this and a good white slag practice, tremendous difference in the quality levels of the steels made out of an electric arc furnace. There's also a vacuum degassing option that was in the set of slides that I'm using. Quite frankly, you would probably never use it for rebar because of the added cost. Just doesn't bring any value. But it's primarily for removing hydrogen as well as deoxidizing and decarburizing. But you don't need it for decarburizing rebar because your carbon levels are way up there. By decarburizing under a vacuum, it's talking about getting carbon levels below 4%, or 0.04%, to try to get carbons down there like the IF steels and things like that. Specialty steels for sheet metals and so on, you would use a degasser, but for rebar at 20, 25, 30, 40 carbon, you do not need a degasser. You might be able to use it to remove hydrogen because hydrogen is an issue that we haven't talked about much yet in rebar production. Not that it creates a problem with the final product in use, but it creates a problem in testing because it remains in the steel for a short period of time after production, usually a matter of days or maybe a week or two. But during that time, it can dramatically affect the ductility of the steel and the results you get on these tensile tests that we extensively talked about yesterday. And one of the variables that controls ductility, elongation, particularly reduction of area of the local elongation, is hydrogen content. Hydrogen in steel, in a typical electric furnace operation, making rebar or anything else, hydrogen content in the steel will be from 4 to 6 ppm. That's more than enough to create serious mechanical property problems. So what you hope is that in the rolling, in the subsequent processing of the steel from liquid metal eventually to the final rolled form, that the hydrogen evolves out of the steel or degasses itself. And it does, but in heavier sections, it takes a lot longer time to do it. So if you're making large diameter rebar, for example, if you're talking in the, I don't know how we go big, we go millimeters, you know, we go to 18 bars, so that's what, 60 millimeters, 2 1/4 inches, 60 millimeters, I think, is up to that size range. One of my first experiences working in a steel mill as a young metallurgist just out of school was to solve a problem of production of large diameter rebar, this 18 bar for a nuclear system, which had all these requirements in it, trying to make 706 in that size, and we weren't making elongation requirements. And after investigation, we identified we weren't because we weren't getting any local elongation, and without the local elongation, we couldn't meet without the local deformation due to necking, we couldn't meet the total elongation requirements. And the reason we weren't getting that local elongation is because of hydrogen. So a simple result, in this case, 100-degree water boiling for an hour, which sounds like a bad thing to do for nitrogen, but for hydrogen, it's a good thing to do because it actually got rid of the hydrogen, and then we met the elongation requirements. And there's actually, in the specifications, there's a clause in there that allows you to do that for the removal of hydrogen, because hydrogen eventually comes out by itself. And so therefore, it's not a permanent problem to the steel, but it is a problem in meeting the requirements on initial testing. So it's a long statement about hydrogen in rebar, but typically it doesn't justify using a degasser to get rid of it. It's way too expensive of a solution. But a degasser would look like this. The most common one used in electric furnace shops is a tank degasser, where you actually just set the ladle down inside of it, drop a roof over the top, pull a vacuum internally, and then stir it with injected argon from the bottom. This is a picture of a degasser station actually in operation with a ladle setting in it. After we're done, and we get the chemistry and the temperature we want, we go to a steel. Is this time? Excuse me, missed that. Sorry, good time to break. Okay, good. We'll come right back to this point. Thank you. Mm-hmm.
Thank you, Bob, for this presentation. We'll take a break for 20 minutes, and after that we will come back. سنتوقف لمدة 20 دقيقة، بعد ذلك نعود إن شاء الله في 10:35 دقيقة بإذن الله. شكرا جزيلا.
يا أخوان، في هنا استبانة.
اي نعم.
فيها ثاني في الملف اللي اعطاكم كان فيه ورقة عن الملاحظات وأي شيء، فنرجو منكم يعني تعبئتها وجيبها إذا تنتهي الأشياء، وإذا ما هذا يأخذها من عند حق الاستقبال.
نعم.
هذا مهمة يا أخوان، عشان فيها اللي فيها ملاحظات وماليات توصيات ضروري نعبي الثنتين. الاستبانة يكون عندها
اطلع فوق عشان يسمعون.
مصانع الحديد متكامله يعني مع بعض.
بدور عليك والله. زي السيد توفيق زي حالك باشمهندس زي حالك كويس تعبناك زي حالك. اخ اللي بيقدم فين المهندس قال لي والله شكله ما جاش اسال دائما المنسق. شوف النكته ازاي
هو نفس شكله برضه
لعيب على الصعيد
نفس شكله هو كمان. يمكن شكل حضرتك
انا من اول يوم سائل عليك والله انا دوختك بالايميلات فعلا.
يمكن شكل حضرتك بيتغير يوم عن يوم فعشان كده حتى
على فكره انا سلمت على المهندس عبد المحسن اوائل 6 سنين يا باشمهندس هم شهاده الايزو الساسو هم اللي عملوا ايدت علينا المهندس توفيق والمهندس عبد ما شاء الله ناس كبيره يعني سلمت عليه امبارح.
قطع زي ثابت يعني ما عاد بشوف.
خذوا الساسو مؤخرا بس المهندس احمد همام ده علم من الاعلام استاذ يعني.
والله يبارك عبد القادر يعني برضه من الناس الاسماء اللي لها اسماء.
انا في اللجنه مهندس السيد في اللجنه.
مهندس اللجنه لا مهندس السيد عن الركحي عن الركحي مهندس السيد قطب. ان شاء الله يكون في.
لكن بعد الموضوع ده اللجنه لازم تجتمع عشان يصير في تعديل في المواصفات صح؟ ان شاء الله.
أنا
Test.
السلام عليكم ورحمة الله وبركاته. نرحب بكم مرة أخرى في ورشة عمل مواصفات وعمليات تصنيع حديد التسليح، ونستكمل معكم الجزء الثاني من عمليات التصنيع، ورقة العمل التاسعة التي يستعرضها الخبير الأمريكي روبرت جولدويسكي. فليتفضل مشكورا. It gives me a great pleasure to invite again Mr. Roberts to present the 9th paper of this workshop to speak about the specifications and also the operations of manufacturing the reinforcing steel bars.
Welcome back, and we'll get started again. So far, we've progressed in the steelmaking operation through the basic melting operations, electric furnace. Of course, we talked about the iron source, the blast furnace versus scrap, and we talked about the BOF and the EAF, electric arc furnace and basic oxygen furnace. We talked about the ladle refining stations. So after we are through to that point, where we are is we have the molten steel at the chemistry and temperature that we want it to be. Now we have to solidify it. And of course, some of the major progress, major advances in that over the last 50 years are kind of amazing. But there are two basic solidification or called casting processes, and the first one is certainly the old way, the ingot casting process, where you simply pour the steel into a typically cast iron vessel of some sort and let it solidify. With the ingot casting process, you could make a few interesting kinds of steel. The first was called a rim steel, where simply the steel was poured, steel which is very high oxygen level, had not been killed, so to speak. That is, had not been deoxidized. So it would have a very high oxygen level. You could pour it into an ingot, and it would then, what they would call rim, which was simply a reaction between the oxygen and the carbon in the steel, forming CO bubbles, and rising up out of this ingot, but meanwhile solidifying the skin that was highly decarburized near the surface of the ingot, of course, right next to the cold mold that you were pouring this steel into. It made for some interesting low carbon strengths. It made products. There's long stories about rim steel and rim steel substitute we tried to do on casters that I'll tell you about someday, but it would take too much time here. You can also make it an ingot cast, and this was done quite routinely for construction, structural type steels, was to make semi-killed steel, which was known to be partially deoxidized but not fully deoxidized. It was done. You couldn't use aluminum in it, but you would use a low level of silicon and get the oxygen levels down to something that was relatively small. You did not get the rimming action you got in rim steel, but what you did is you had enough foaming at the final solidification to have a whole lot less internal piping, it was called, in the ingot, where you could improve the yield of steel made in a given ingot, usable steel in an ingot if you made it semi-killed. Or you could make it fully killed, which was enough silicon and or aluminum to get the oxygen down to a point where during the solidification process there was no evolution of carbon monoxide, which is basically the definition of killed steel. But after solidifying in an ingot, of course, you had to roll it to bloom or billet before you did your rolling, whether it was a slab or bar. Of course, for bar production and rod production, long products, these ingots tended to be basically rectangular in shape or square, fairly high vessel, and you would roll them to a bloom or billet. And of course, the biggest problem with ingot casting is the high yield loss that went with it. There was a lot of scrap generated in the process, and it was not economically viable compared to the continuous casting processes that started up about in the late 60s and 70s. And they pretty much took over the world with respect to the solidification process for steel. It is interesting that the ASTM A10102, which is the structural steel for bridges, buildings, rolling stocks, and ships, recently changed all their structural specifications to require killed steel. And I know that because the chairman of that committee asked me to lead the task group to get this done. So it took about 2 to 3 years to go through all the specifications and rewrite them. So now all of them required killed steels. But in rebar, it's not required. So you could still make rebar out of ingot cast, semi-killed steel if you so wish. And it could still be done. There's nothing specifically to restrict you from doing so. A continuous cast product will continuously produce a solid section, usually square, but maybe rectangular, and which is withdrawn from water-cooled copper molds that you actually pour the liquid steel into. The dimensions of these cast sections, sorry I got it in inches here, but let's do a quick conversion. 100 by 100 millimeters is usually about the smallest one made, and can go up to, in billet form, up to 200 by 200. Or it can cast blooms, which can be substantially larger than that. The characteristic of blooms versus billets, at least in my definition, is a bloom will require 2 rolling operations to get it to the final product, where a billet can be rolled in 1 continuous operation to final product form. I appreciate your nodding. You're understanding what I'm saying. This casting process, of course, has to transfer the liquid steel from the ladle to a point where it can solidify. And it can be done through open stream flow, through metering nozzles in the tundish to the mold. And you would typically use an oil lubrication in the mold to ensure that the steel, as it solidifies, does not stick to copper walls. This process, which would typically be used for rebar production, operates best with silicon killed steels. If there's aluminum present in the steel, it will reoxidize easily from the atmosphere, causing all sorts of problems. The clogging of the nozzles, formation of inclusions that get to be real problems. But you can, to some degree, control the reoxidation of the steel while going through a metering nozzle, usually by using some sort of gas shrouding, nitrogen or argon, whether it be in a bellows shroud or using a submerged nozzle, ceramic submerged nozzle, and which usually requires a powder cover of the liquid steel in the mold to prevent reoxidation. And it also provides lubrication by the powder melting, forming a liquid that provides lubrication during casting. The problem with using a submerged nozzle is you need some alternate kind of flow control device, usually a stopper rod from the top in the tundish itself, or slide gates, as opposed to a metering nozzle, which is simply a ceramic piece with a fixed diameter. The submerged nozzle is the way you would normally produce an aluminum treated or aluminum killed steel. And with the powder casting process, you're capable of producing significantly better surface quality. You can maintain the surface quality issue much better. Segregation control can be usually done through superheat control, but you can also add electromagnetic stirring during the solidification process, or you can go to what's called intensive cooling, certain section sizes that's fairly effective at reducing segregation in the final solidified billet. And segregation here is segregation primarily of carbon, but of also other elements like manganese, which tend to segregate to a great extent, which can be a problem in products like wire products where heavily segregated centers do not draw very well. In rebar, not a very bad issue at all. Usually you can live with it. So as we said, rebar is a pretty easy product to make. All these things that you can do with steel making today, typically you don't have to do in rebar. For production rebar billets, casting is often done, most often with open string casting. And sometimes without any gas shrouding, simply open stream, which means that the hot metal, the liquid metal, is exposed to the atmosphere and the oxygen, and you will get some scum forming on top of the mold. It will get trapped in. It will be an exogenous inclusion. But for rebar, again, not a serious problem. It is for rod products, and you continue to fight that. Aluminum cannot be used as a deoxidizer in this kind of casting process because, again, it reoxidizes way too easily. This is a schematic of what a casting process looks like. Again, you have the ladle. This is the same ladle that you put the steel into back at the original BOF or electric furnace. You went to your ladle metallurgy station, treated the steel while it was in this ladle, and then you take that ladle over to the caster itself. Then you have to transfer the liquid molten steel from the ladle through the ladle to tundish shroud. And usually there almost always now people use this, but in rebar you would not have to use a ceramic shroud. You could do an open stream flow from the ladle to the tundish itself. The tundish is nothing more than a intermediate vessel to hold the steel that you're casting for a short period of time to maintain a constant level, which then maintains the constant flow speed through the metering nozzles. And you maintain a constant level by a flow control gate that's usually at the bottom of this ladle here. So the steel flows through here, you maintain a constant level, which maintains a constant flow through the tundish. You can also do some metallurgical things in this tundish in terms of trapping inclusions, things like that. Again, with rebar, not particularly important. Then you transfer, in a similar fashion, the molten steel from the tundish to the actual solidification mold. And that's where it can be done open stream. It can be done with ceramic nozzles. It can be done open stream, but with a bellows shroud around it, which is common in wire rod production. But for rebar, you don't necessarily need to use anything. You may choose to for operational reasons, but not necessarily required to meet quality expectations in rebar. Of course, once the steel gets in the mold, then you start to solidify the shell. The surface of the liquid steel at the top here, if you're using a submerged nozzle, you will put a powder on there that actually prevents reoxidation of the steel. If you're using open stream, there will be no powder. You will simply have that liquid steel exposed to the atmosphere. But you start to solidify the caster mold itself, which is this piece right here and over here. It will be made out of copper. It'll have a lot of water running behind it for very fast heat extraction from the steel to get to solidify, to form a shell on this piece as you're pulling it out of the mold. And so even though as it exits the mold and starts to come down here, the center, the middle part of that billet will have liquid steel, but the outside will be solid, and that will hold that. And you will have rolls that help maintain the shape of the billet that your cast billet or bloom you're casting, to keep it from bulging due to the high temperatures, etc. Meanwhile, there'll be spraying water on it, water sprays, and to again remove the heat, so that you complete the solidification. Solidification process completes as it comes down through this curve, and hopefully is done before you get to the point where you actually cut off the slab or billet, and it goes from there. So that's the continuous casting process. This shows an example of pouring some steel from the ladle to a tundish. Just it's how it looks in real life, one of the ways. This is where you're transferring the steel from the ladle to the tundish, ceramic shroud you attach to the bottom of the ladle. Again, showing it going, another example of the ceramic nozzle with the steel flow. Now we're looking at the tonnage to mold transfer, which is the second transfer process from the tonnage, which is again a holding station for the liquid steel, down to the solidification process. This is probably a slab casters. You see a lot of the mold powder sitting around that it's actually manually pushed in to keep a level of this mold powder on top of the mold as it's solidifying. Another alternative, this is common for rod products, you use a flexible bellows shrouding here, because one of the things that's happening is a mold is always oscillating, going up and down, to make sure that the steel doesn't stick to the side of the copper mold. It always keeps that moving because it's being extracted at a very slow rate, but this oscillation is going on at a fairly rapid rate. And so you need some flexibility because the tonnage is fixed, but the mold is moving. So you have a flexible shroud. And then you inject the argon or nitrogen gas in there to reduce or prevent reoxidation. And after it's solidified, this is the billets coming out of the caster, coming down and cooling. Remember that internally in these billets, it's probably still liquid. But you've been water spraying that. It's getting down to the point, where it's almost all solid. Just another view, it does get down to the torch points, and here you're actually cutting the piece. Of course, you don't want liquid steel in the center at this point because it will just flow out over everything. So it must be solidified at the point where you cut it. But then you end up with the billets. And that's now your semi-finished material coming from the steelmaking process to go to the rolling process. This is what they will look like when they're stacked outside waiting to be sent to the rolling mill. You can hot charge these, take advantage of the temperature that's in those billets and put them right directly into to the reheat furnace or holding furnace for rolling without cooling down to room temperature. But there are complications that go with that are interesting in terms of what happens to a lot of stuff in the steel. The grain size control, for example, the precipitation of aluminum nitrides, so on and so forth, things that we get heavily into when we get involved with processing with the new CSP mills for slab casters. But a lot of new bar mills are also trying to do this, direct charging, maintain the heat, the energy that's already in these billets that are just being lost, make use of it safely. So we get to the rod and bar rolling process, very similar. First you have to heat them if they're not already hot. Most billet and blooms are cooled to allow transformation from austenite to ferrite perlite before rolling. This provides a certain amount of grain refinement to the billet that you would not get in a direct charge process. But you can surface quench it to get the same effect on the surface where the problems are. And there are some processes to do that. It's reheated in usually a natural gas-fired furnace, can be oil-fired furnace, can be solid hearth in the bottom, can be walking beam, various different kind of heating operations. But a large furnace that heats up all the bars to the final rolling temperature, which can be typically 1200 to 1300 degrees as be a normal rolling, preheat rolling temperature for rebar. Metallurgical concerns at this point during the reheating process includes things like decarburization, again, not a problem for rebar. Dissolution of the precipitates, this would be a problem if you're using, for example, niobium as a microalloy. You'd have to make sure you got your temperature high enough to get it in solution. If you're running, as most people do with rebar and electric furnace, very high copper, you want to maintain a fairly high reheat temperature to minimize hot shortness problems. So this would be a typical view of a billet reheat furnace, and the exit, the billet would be pushed out of the furnace as it gets through. It's charged on the other end, slowly walks through the furnace, and then pushed out on this end. This shows simply a push-out exit. as opposed to slabs that maybe drop out of the end. And with a big door, this allows you just to have a smaller door, less heat loss, and it comes directly out of there to go to the rolling process. In the rolling process itself, it can have multiple strands, although today most bar mills only have one. Some rod mills will have a two-strand operation, which means you only have one continuous rolling process. The roll passes can be any number depending on what your starting billet size is and what your finished smallest roll product diameter you want to do. But a typical rolling mill will have anywhere from 20 to 30 actual rolling stands. Pass design is usually an oval round, but box can be used, particularly on the initial size. And again, the various preferences there. Finish speeds on a rod mill can be up to 120 meters per second. They're not nearly that fast on a bar mill, but in all cases, the maximum finish speed limits the starting section size, because if you can only, in a rolling mill, once you start the rolling process, there is a fixed volume of steel that can pass at any point at any time. So a bigger section has to go slower, a smaller section has to go faster to maintain the same volume per unit time. And there is a limit to how fast you can go. Up to 7, this is 175 millimeter, but a typical billet size for a bar rolling operation might be anywhere from 130 to 160 millimeters square. Larger sizes can be direct rolled if their rolling is discontinuous. We had a rod mill in Kansas City we worked with that actually rolled 200 millimeter billets direct rods, but in order to do that, you had to have a discontinuous rolling process where you actually rolled the 200 millimeter down to about 100 millimeter square and then separated it so it wasn't linked. So then you could start the next rolling process at a slower speed so that your final speed was not exceed the capability. You may have the high pressure descaling system ahead of the, as you drop out of the furnace, if you want to control scale. Again, not a problem with rebar. The rolling mills can have a lot of different directions. This is a large rolling mill, horizontal, vertical, which means you don't have to twist it. The original rolling mills required you to twist the bar after every second stand because you may roll, if you're rolling diamond square or you're rolling oval round, there's always one roll pass that the long side has to be turned up on edge to hit the next roll stand. But if you have horizontal vertical mills, you don't have to do that. There's also Cook's mills, Cox mills they call them, which is 3-axis mills. The advantage of these is very good size control. Typically you would not have one on a rebar mill. That's just another view of a Cox mill. This is what they call the finish block or the Morgan block for a rod mill. They wouldn't use these for straight bar, but for a rod mill, these are very high-tech machines because the finish speeds coming out of there can be as high as 120 meters per second. So we're talking very fast speeds. So I think calculated somewhere around 400 kilometers per hour kind of speeds at the finish end of these things. Though you would roll a bar and coil would go through a machine like that, but straight bar typically would not. This is an example of a 2-strand rod mill. I mentioned that you may be running two side-by-side processes. This is another view of a smaller end of a bar rolling mill. Again, horizontal and vertical roll stands that you can see. Always a lot of water being splashed around to keep the equipment cooled. To some cases to get temperature out of the bar if you so choose, but typically that's done on a bar mill. This is something unique to rebar, really, for the most part, is the ability to split. As I said, rolling mill productivity and finish speeds are controlled, the productivity of a rolling mill is controlled by the maximum speed you can finish at and the section size that you're rolling. So if you're rolling small diameters, it really can cut back on the productivity of a mill. The rebar mills have solved that by actually splitting a bar, as you can see it up here, and rolling, or up here, and rolling it flat, and then splitting it into multiple bars down below, as you see here, up to 5 small bars out of 1 large bar. The advantage of that now is I can get a lot more mass per unit time with 5 bars finishing than you do with 1, and you can improve the productivity of your mill substantially. This just shows another example of going from 1 piece to anywhere 2, 3, 4 pieces, various profiles. And of course, the reason is your productivity, which is on this chart, can be a constant rather than diminishing rapidly as your bar size, your product size goes down. It seems backward to me, but that's what this is supposed to say. Of course, after you finish rolled it, then you have to cool the bar. Most rebars, if it's hot rolled, traditionally it's just simply air cooled. You can also control the temperature during the rolling process if you're trying to do the so-called fine grain or controlled rolled processes. You can also do water box cooling immediately after the last pass to control grain growth and scale formation, and try to impart a finer grain size and higher strength, even without the quenching. Or you can do the QNST, as we say, the quench and self-temper process, also known as Thermex, also known as TempCore, all of which simply are getting the quench ring on the outside. Subsequent control rolling after cooling in a rod mill is done at a rod mill will go through the laying head, and then you optimize the metallurgical structure through some sort of combination of forced air cooling or hot water cooling or insulated slow cooling. In a bar mill, the water box cooling is used for the quench and self-temper process, as I said, forming a martensitic shell, which is then auto-tempered by the residual heat internally in the bar. This shows a couple examples of water box cooling. Probably these are actually on a rod mill, but they look very similar on a bar mill to get this quenching process done. So it's simply getting properties to the extensive use of water and water cooling. You end up with a product that looks like this with an outer shell of tempered martensite and inner shell of ferrite perlite. The temperature profiles, of course, for a QNST process are like this, where the core goes through this continuous transforming into ferrite perlite at looking like this. The surface goes down past the MS start, forms martensite, and somewhere in the transition is a point where it just comes down but doesn't quite form martensite, then it goes through this. And then, of course, you do get a lower transformation ferrite perlite during this process as well. All part of doing the QNST. This is just a standard cooling bed process where you see the bar come off the rolling mill hot, and it's air cooled on the cooling bed itself. This is a rod rolling process. This is the laying head that rolls the coils down and is capable of then taking a much higher finish rolling speed and then doing a control cooling on what has kind of become air-cooled deck, or Stellmore deck as it's known pretty generically now. I spent a lot of time working in this as a high-carbon rod metallurgist for many years, so very familiar with these particular cooling processes. This just shows, again, from a metallurgical standpoint, what you're trying to do with this process. You're trying to get it down, cool it down to get it to the nose of the ferrite perlite formation to get as fine a possible perlite, but do not get it down to the bainite or martensite regions. Whereas just air cooling may come up here, which is safe from forming any martensite, but the perlite, you can get grain growth in coarse perlite, which lowers the strength. Simply on a rod mill, of course, you're worried about air distribution to get uniform cooling across the deck. This is an air fan that's used to cool these rods on a Stillmore deck. You worry about air velocity. You try to get the velocity on the edges where all the mass is, and that sort of thing. This is what the rolls of the Stillmore deck look like as they take this hot product and run it through there. You can, centering the bar is always a problem. You can use a rollarized center arm. You can change the speed, usually using steps in the rolling process. And then you have the finished product, in this case, the final coil, if you're coil the bar, and so on. But for rebar technology, of course, if you look at overall rod and bar process, these are the quality characteristics you have to impart on the product in the hot roll condition, including chemistry, inclusion, surface quality, segregation, size control, microstructure, and mechanical properties. But for rebar, it's primarily, of course, if you have chemistry requirements, which are generally not hard to get, but you have to meet those. The microstructure has to be appropriate to meet the mechanical properties you're trying to do. There is no microstructural requirement in rebar, as there isn't in most specifications. But metallurgically, you have to understand, you have to get the right microstructure if you're going to get the right properties from a given chemistry. Yes? I don't know of an application. Obviously, I'm aware of the wording that you're talking about, and it's pretty loose. I've never heard of rebar being rejected due to surface quality, as long as it makes the bend test. Basically, if you can fabricate it, they'll use it. So it's really the deformation during fabricating where surface quality issues, and they have to be pretty bad to cause a problem there. So that's why things like you can go to higher copper levels, a few scabs and slivers really don't hurt the performance of the product. If you make the it's just like the chemistry issue. It's not really important if you make the mechanical properties, and that's the tensile and the bending. If you can do those things and fabricate the product, it's probably going to work.
So the key point here is as long as the rebar meets the mechanical property specifications, the weight, it's okay, and you should not be worried about those characteristics like rust or seen on the rebar surface. Yeah.
Yep.
Thank you.
That's my interpretation of that. There may be some people out there that have a different one, but
we need opinions only.
And I've certainly not heard of any. I've been involved with a lot of products where surface quality was important, and we had to deal with a lot of things, but it's never happened in rebar unless it's so obviously bad. The rib? Yeah.
Effect, then shall be testing the mechanical test and check about the diameter and weight.
Usually in the ASTM there is a limit for rib height, spacing. Okay, if this is deviated from this is yes, this is. But his question, okay, regarding one of the standard ASTM 615 said rust seem not cause for rejection. With the customer receive material with this color material or rust or some this is a line crack on the cross rib on the okay, he's complaining. Okay, as per ASTM, not cause for you, whether to accept, not here the debate starts.
كاستمر يكون يقدر يرفض إذا كان نفس الصدى مؤثر. بعد الإزالة يكون لازم يتأكدون إن هذا الصدى ما أثر ولا هذا، ولا هو قال تشتر ما هو يتغير، يمكن اثناء ازاله الصدى هذا يتاثر في كذا، فلذا في المواصفه الملكيه الاولى احتاطوا انهم يكون لازم يتاكدوا منه. لا يمكن ياثر، يمكن الازاله اثرت بعد اختصاص، فلذا المواصفه الملكيه اشترط ان بعد الازاله يتاكدون من يتحقق من المواصفات.
Please.
Rebar that we manufacture as a supplier is to be sold out. Is sold out, and it depends on the application that he's using. If he's using these rebars as a black rebars for construction, these minor surface defects like seams or slivers or discoloration obviously should not matter. But if he's using for epoxy coating, obviously the other ASTM standard 775 comes into play.
Yeah.
And therefore, what is good for a black rebar is not good for epoxy coated rebar.
Oh, yeah.
Similarly, if the corrosion affects the mechanical strength or the rib heights, obviously that would call for rejection.
Yeah, that's right. All those things. That's right. If you're going to coat it, then it becomes more critical, and you would have to make a judgment accordingly. It is not explicitly defined in the specification. And I think that's where common sense comes into play. I mean, you gotta have an acceptable workmanship surface for the application you're going to do. And again, black application in construction is just not critical. But if you're coating it, it becomes a whole lot more critical.
But there more difference between the corrosion and colorless for the bar. There's more difference between the corrosion in the bar and the colorless
colors or
this color.
Yeah.
Rust. There's more difference between the different.
Well, corrosion, of course, is something else. Yeah. Yeah. If corrosion affected it to the point where you couldn't no longer meet the properties or the deformation height or something like that, then it's a problem. But if you still meet all those, it's not a problem. But of course, that's not in the manufacture. That's in the subsequent storage and handling of the material, where you get corrosion and stuff like that. It's sitting out somewhere in some bad environment. Yep.
During the process of steel to produce coil, there is a lot of quantity of scale coming during the operation with water. Scale.
Yeah, scale formation during the hot rolling process, yes.
Is there any limit for this scale in ton? And also in the finished product, after the cold drawing, there is also another quantity coming around 10 kg to 12 kg per ton. But in the process of coil, in the initial, is there any range or also in finished product? Scale per ton.
Okay, you're talking about scale formation in coil, meaning a rod mill kind of approach. Are you talking rebar or wire rod? Coil, Yeah. Rebar in coil. Yeah. Obviously, there isn't any specification for that, but typically a rod mill has the ability, through the combination of the water boxes, to probably get better control on scale than you would see even in a standard hot rolled bar mill. Of course, if you're water quenching it, doing a QST, there's probably not a lot of scale on that. It's pretty much what did form is gone. Scale weights, typical scale weights on product rolled at a rod mill, and that would probably include rebar as well, although I don't know if anybody really has been concerned enough to measure that. But on a rod product, a typical scale weight on the product is on the order of 0.5% to 0.7, 0.8 would be a typical mechanical descale scale weight. If you're doing chemical descaling and use a lower laying head temperature, you could get that scale weight down to 0.2 to 0.3%. That's percent of the total mass of the product is scale. So that's a typical scale weight on a hot rolled product off a rod mill. So I would use 0.5% as an answer to your question. And it's going to be pretty difficult to get much different than that. And that's certainly expected and typical and not a problem.
By controlling the laying head temperature itself. So that could be an answer for him that the lower laying head temperature is giving a good performance for the scale layer formation itself. So if you have a problem for this, try to control the laying head at the lower degrees according to the standard of the material you are using for the final product. But anyway, you shouldn't have a scale formation in the wire rod, especially in the finishing area, if you are controlling well the two things. First, the laying head temperature. Second, the intensity of the air cooling, especially in the first stages of the Stelmore conveyor.
Yep.
Okay, thank you.
Yeah, in rod products, you would be concerned about that to tailor the scale depth for the cleaning process used, descaling process, whether it's mechanical or chemical. And you do that by, just as you say, primarily the laying head temperature. After all, the Stelmore deck, as I showed you the picture of, was originally designed for the purpose of reducing scale loss. And it does that by using those water boxes to get from the finished rolling temperature, which can be quite high in a rod mill because of the speed of the final rolling process. You want to get that down to a temperature that's still above the transformation temperature but close to it. So then you put it on the Stelmore deck and even forced air cool it. All of that is intended to minimize the amount of time the steel is exposed to the atmosphere at high temperature, which then minimizes scale formation. There's one of the things when we talk about surface quality is ball quality, is the effect of copper. Certainly when you get into rebar production, we'll talk a little bit more about various alloy systems and so on. But with copper, you do have the hot shortness issue. This slide is simply here to demonstrate that there is an effect of copper on, in this case, it's the axis here is called rate of formation of a copper layer, but what it really amounts to is the faster you form this rate, the more problem you're going to have with copper hot shortness. But the key is there's a peak temperature around 1100. And one of the ways to avoid copper hot shortness in a bar rolling process is to raise that temperature to get above 1200 to 1250. Substantially less issues with copper hot shortness than you have at this lower temperature. And believe me, I've learned that to be absolutely true with rod mill operation for many years. So, and I have all sorts of stories about how we demonstrated that. But this curve is real. It does work. It's contrary to conventional thinking that, well, you should reduce the temperature to minimize copper rod shortness. It's just the opposite. You need to raise the temperature. Yes. Copper, well, as we know, tin is well known as being, it accentuates the problem. But typically, from a residual standpoint, they go together. And so mostly you just use the copper level as the criteria. Carbon? Okay, yeah. Yeah, we have stories with nickel additions too. Yeah. Conventional thinking is add nickel 1-to-1 with the copper and you can avoid copper hot shortness. And that's been done in some alloy systems. Believe me, you can't afford to solve your copper problem that way because it costs way too much. Yeah. And again, we've actually, it wasn't my idea, it was somebody else's to try it. At 0.5%, you know, half the copper is, half the nickel content is the copper. It wasn't effective and it cost a whole lot of money. So yes, you can do that, but it's only if you really have to have high levels of copper in the steel for some other reason, you would add that nickel. Today, almost nobody does it because of the cost of nickel. Silicon can do it as well. So silicon is an alternative that's not so expensive. You can add silicon to reduce copper hot shortness. Yeah. There's a long story on that one, too. Yeah, it's all the electric furnace guys that charge you extra for 20 copper minimums when they're getting it for lower cost than they would at lower levels, but that's another story. Yeah. Copper, typically a weathering steel is considered to have a copper level of 0.2 or greater %. And of course, in rebar, electric furnace, that's a low level of copper. A more typical copper level in rebar is 0.4 in the U.S. I got some data to show you later on that. So all we're saying here is, yeah, copper can cause hot shortness, but you can learn how to live with it. And other than that, copper has almost no negative side effects in steel other than this problem. It does add hardenability, but you just compensate with, well, I don't need as much manganese. And speaking of, this is, I guess this is where I put the slide. I know I put the slide together and said, when do we get to it? We got to it right here. I went to my database. I've got my computer, I've got rebar chemistries from a whole lot of different producers around the world. I selected this one. This is a U.S. Matter of fact, I lost the identity. I'm not sure who I got this from, but it's typical of an American producer of straight bar. Yeah, this is hot rolled. It's a combination of 706 and 615, but most of it's 615. Probably 80% of it was 615. But it was over 17,000 heats. So we're looking at many years of production of rebar. And just look at this. And so I'm just showing you the average, the min and the max of these elements over that very, very long period. And the key, some of the things, of course, you see some, when you look at that many heats, there's going to be some real flyers on your min and max, like copper 97 as a high. That's unusual. Average was 39, and typically the range would be 30 to 50. Seldom really get over 40 much. But in the 40s they're comfortable with, over 50s they get uncomfortable. But, you know, there's some very low coppers in there as well. Okay. I think I'm about done with this. Timing is good. Manganese level, in this particular case, most of it was 615. He's running about 1%, but that would vary depending on the size, and he has all his different sizes in here. Vanadium content, he wasn't adding a lot. He was adding on course 706, he was adding 0304, but traditionally a lot of the larger diameter 615, he would add 02, vanadium to. But the smaller sizes, he wouldn't add any. Running manganese all over the place, but typically around 1%. 706 would be higher than that, and we'll talk about that. So this gives you an idea. So you can see he was averaging a 66, which is a good average for grade 60. There was some grade 40 in there. Highest one he saw was 96, so there may be some grade 80s in there, 75. But I just did this to show you that, you know, people make a lot of steel at these copper levels and really not have a problem making rebar. It's not unusual at all to have these kind of chemistries. For tin? Yeah, that would have to be a real flyer. Yeah. He probably had a problem with that heat. You don't see that very often unless there's a huge amount of, yeah, that would be a problem heat. Yeah. But as you can see, the average is, I don't even know what that was rounded off, but typically it's not there. With that many heats, you get a flyer occasionally, and there must have been something in one heat. It's only one heat out of 17,000, so yeah. As I said, don't be alarmed by those numbers. It happens every once in a while. That's not typical. So that's it. So I think that would be good break time. We'll go with this.
Special thanks to the American expert, Robert Godrisky. And now we'll move on and proceed on with our lectures. الإخوة الكرام، للمصانع السعودية تجارب في مجال حديد التسليح، حيث سيستعرض لكم سعادة المهندس أحمد همام مدير الدرفلة بشركة حديد الراجحي هذا الأمر. ونبذة عن المهندس أحمد محمود همام. تخرج من كلية الهندسة جامعة الإسكندرية عام 1988. حصل على درجة الماجستير في الهندسة عام 2001 من جامعة الإسكندرية في التحكم بالخواص الميكانيكية للحديد المدرفل على الساخن. حصل على تدريبات متخصصة في مجال الدرفلة بأمريكا وألمانيا والنمسا وكندا. عمل بشركات الحديد بمصر والسعودية لفترة 26 عاما من الخبرة، ومنذ عام 2008 يعمل بشركة الحديد للراجحي كمدير للدرفلة. فليتفضل مشكورا.
الحمد لله والصلاة والسلام على رسول الله. إن شاء الله نبدأ البرزنتيشن بتاعتنا. يعني كنت متحير أبدأها بالعربي ولا بالإنجليش، لكن يعني هنخليها بقى فرانكو أراب بقدر الإمكان، لأن معظم المصطلحات غالبا هتكون بالإنجليزي، لكن إن شاء الله هنتجاوب بالعربي مع الجميع بإذن الله. لما نتكلم على شركة الراجحي، احنا ان شاء الله في عندنا مصانع موجودة في جدة وفي الرياض، وهنتكلم على المصنع اللي يعتبر احدث مصنع تم انشاؤه في جدة بطاقة مقدارها 1,000,000 طن في السنة، وده بيعتبر واحد من 4 مصانع على مستوى العالم اللي هم بينتجوا هذه الطاقة اللي بتمثل 1,000,000 طن كمصنع واحد بفرن واحد. ووضعنا فيه يعني ستيت اوف ارت لكل ما هو موجود في عالم الدرفله، بحيث ان احنا نقدر نوصل لما هو افضل مع سواء اذا كانت الكواليتي او التنميه اللي احنا بنطلبها في شركه الراجحي للوصول للطاقه القصوى، سواء بما يمثل 2,000,000 طن لجده والراجحي مع بعض. طبعا الطاقه القصوى اللي احنا بنحاول نوصل لها ده ناتجه من مجموعه الميجا بروجكتس الموجوده في المملكه، بالذات في المنطقه الغربيه والمنطقه الوسطى. فكان في اتجاه ان احنا يكون اللوكيشن بتاع المصنع ده مع الميلك شوب الموجود عندنا في جده، بحيث ان احنا نقدر نستفيد من كميه البيلت الموجوده اللي بتصل حوالي 850 الف طن في السنه، واستهلاكها في هذا المصنع. وايضا من الحاجات اللي احنا كنا بنبص لها اللي هي عمليه تدريب الكوادر السعوديه على احدث تكنولوجي ممكن تكون موجوده في مجال حديد الصلب في العالم. نظرتنا للمصنع ده كانت مينلي ان احنا بننظر للسوبيريور كواليتي اللي احنا نقدر نحصل عليها، مع محافظتنا على الانفايرمنتال اسبيكتس الموجوده في مصانع حديد الصلب. المعروف ان هي دايما بتكون محتاجه لسبيشال كير للقائمين عليها. يعني لما هنتكلم على البروجكت بتاعنا ده، احنا بنتكلم على مصنع قائم تم التفكير فيه في سنه 2008، وتم عمل الدراسات المبدئيه بتاعته ووضع الجداول الزمنيه للتنفيذ استغرقت حوالي 22 شهر، وتم التنفيذ باليوم طبقا للجدول اللي كان موضوع لبدايه تشغيل المصنع. طاقه المصنع زي ما قلنا مليون طن، 730 ألف طن من الريبارز و270 ألف طن من الكويلز. المقاسات اللي بيقدر تيجي في البار ميل من 12 ملم ل 40 ملم، وبالنسبه للواير رود في البلين واير رود from 5 to 0.5 to 60 ملم، وبالنسبه للديفورمد كويلز from 6 ملم to 60 ملم. والماكسيمم كويل ويت اللي نقدر نضرفله ونعمل له هاندلنج داخل المصنع هو 2.4 طن. بريفلي المصنع بيتكون من ووكينج بيم ريهيتنج فيرنس 200 طن في الساعه، وده بيعتبر من ضمن الكاباسيتي العاليه جدا في الافران الريهيتنج فيرنس. وبنقدر نستخدم فيه بيلت من كروس سكشن 150 في 150 و130 في 130 باطوال لغايه 14 متر. الخط بعد كده بيتكون من كونفرتبل ستاندز 16 ستاند فيرتيكال هوريزونتال، منهم 2 كونفرتبل، وفي 2 بي جي في او بنسميهم اللي هو الهاي فينشنج بلوك او مورجان بلوك زي ما برضه معروف بالاسم ده، للبار ميل بيحتوي على 4 ستاندز ايتش، وبالنسبه للواير رود بيبقى 10 ستاندز. في عندنا كوينشنج سيستمز للحصول على اعلى معدلات الجوده ايفن للبار ميل او الواير رود، سواء اذا كان بالكيو تي بي او الكيو تي ار بالنسبه للواير رود، نهايه بكولينج بيد 100 متر في البار ميل و100 متر برضو على الستيلمر كونفير. السرعات الماكسيمم اللي بنشتغل عليها 35 متر لل بار ميل لغايه مقاس 12 ملم، ودي تعتبر من المقاسات يعني مع السرعه 35 متر في السليتنج بروسيس، فبنحقق فيها اعلى انتاجيه بتصل لل 200 طن ساعه. وصلنا تقريبا 106 متر للواير رود رولينج سبيد. المصنع عنده كابابيليتي لانتاج الستيل جريدز المختلفه بالانترناشونال ستاندردز الموجوده، وبالنسبه لنا طبعا الساسو 2 اللي احنا اوريدي اندر بروسيسنج فيها في الفاينلايزنج السيرتيفيكت، وطبعا الاي اس تي ام ايفن ال 615 او ال 706 والاي اس تي ام 510 للاي زي جريدز من 1006 لغايه 1065 البريتش ستاندرد، وكل الدكتايل ماتيريالز على الايزو 69352. يعني ده مفيش مايك او حاجه في بوينت، هو محتاج مايك بس لان اتحرك. البوينتر ده شغال؟ اشتغل ازاي؟ بريفلي اللي اوت للمصنع اللي هو السي بي ار ام اللي هو الكومبايند بار اند رود ميل بلانت، بيبدا من منطقه للكونكشن مع الستيل ميكنج الحاليه الموجوده، لنقل البيلت ايفن على الكولد تشارج او الهوت تشارج. ودي تعتبر واحد من البينيفيتس الموجوده في المصنع، ان احنا نقدر نتعامل مع الهوت تشارج بغرض توفير الفول وبغرض تقليل عمليات الهاندلنج اللي بتتم بالكرينز. بعد كده في منطقه الفرن، الطاقه بتاعته 200 طن ساعه. بعد كده عندنا ديسكيلر يونت ويز هاي بريشر ووتر جيت بيصل لحوالي 250 بار. ده to decrease the scale formation during the process of the rolling itself. بعد كده هنعدي على الستانس بتاعتنا اللي هي 16 ستانس، وبيتم بعدها سليتنج في البار ميل على 2 بي جي في او فينشنج بلوك، ثم الكولينج بروسيس على الووتر كوينشنج، ثم الستيل مور كونفيور، ونقلها بعد ذلك على محطات الستيشنز الخاصه بالتاينج والفينشنج فاسيلتي. بالنسبه للواير رود، بعد خروجه من ستاند 16 بيتجه للفينشنج بلوك ثم الستيل مور كونفيور ثم الهاندلنج لمرحله الفاينل برودكت كويلز. دي صورة عامة عن فرن إعادة تسخين اللي هو 200 طن ساعة. برضو صورة عامة عن الرولينج ستاندز فيرتيكال هوريزونتال ارينجمنت. دي الكوينشنج لاينز اللي احنا بنتعامل عليها. هنشوف هنا دي الكوينشنج لاينز الموجودة لللاترال لاينز في حاله السليتنج، او في حاله السنترال لاين خط منفصل، والواير رود في الاتجاه الاخر. الكولينج بيد بطول 100 متر. ده الفاينل برودكت ستورنج اريا عندنا للبار ميل، وده بالنسبه للواير رود. والواير رود يعتبر مجهز بريتاردد كولينج كونفيور لانتاج السبيشال ستيل جريدز الموجوده في الواير رود، بغرض اذا كانت الواير دروينج او كولد هيدنج او للويلدنج الكترودز وكل الاندستري ابلكيشن سبسيكوينت اندستري ابلكيشن مطلوبه من الواير رود. بنحاول دايما نعمل الهايست كواليتي ليفل، وده التارجت الرئيسي عندنا في المصنع. الهايست كواليتي ليفل يعني ايفن اذا كان في ستاندرز لسي وليكن الاوفاليتي مثلا 0.6 اكسبتد، فاحنا بنشتغل اراوند 0.3 يعني هاف اوف ذا ستاندرد على الماكسيموم. عشان كده we are fully confident about our product ان احنا بنقدر نحقق فيه اعلى من المواصفات ايفن اللي مذكوره سواء اذا كانت اس تي ام او الساسو او وات ايفر. ده الستورنج بتاع الفاينل برودكت للكويلز داخل الستورج اريا في المصنع. اذا نظرنا للمصنع فاحنا ممكن نلخص بعض النقاط اللي بنسميها improvement and modifications في السي بي ار ام عندنا، بغرض السستينابيلتي كجزء كلنا بنسعى له في صناعه الحديد والصلب، وبغرض ان احنا تكون عندنا establishment لاعلى درجات الكواليتي اللي احنا موضوعه بالنسبه لنا كتارجت. فبدانا في اول حاجه اللي هي الهوت تشارج ابلكيشن، وتاني حاجه الهيتنج فيرنس ثيرمال اوبتمايزيشن موديل. ثالث حاجه عملنا كومباينيشن اوف ابرون سيستم مع التوين تشانل ده اثناء عمليه الضفاره في البرميل. في نقطه كمان ان احنا عملنا رولينج سايز 20 ملم سليتنج اون سنترال لاين بيسايد اللاترال لاينز وهنتكلم عليه. بار كات اوبتمايزيشن سيستم، شورت بار ريموفينج سيستم، وار او سيستم. الايتمز دي كلها يعني كان بينظر اليها ان احنا بننظر للهاي فليكسابيليتي للبرودكشن بالنسبه للمصنع عندنا. وده هيبان معانا في انتاج المقاسات الكبيره والمقاسات الصغيره او انتاج نفس المقاس باكثر من وسيله على نفس المصنع، وده بيساعد على الحصول على افضل النتائج للعمليه الانتاجيه. في نفس الوقت بيدينا اوبتمايزيشن للبلانت كوست، لان احنا الستوبج تايم بنحاول يكون في اقل وقت ممكن مع تقليل نسبه الهالك او زياده نسبه اليلد، بما يسمح ان احنا يكون عندنا اوبتمايزيشن للتوتال كوست. النقطه المهمه بالنسبه لنا واحنا بنؤكد عليها تماما اللي هي الاوبتيننج هايست كواليتي ليفل with target of zero customer claims. والسلوجان ده مش مجرد ان هو شيء موضوع بنتكلم ان احنا بنسعى ان احنا ننتج هايست كواليتي هايست كواليتي هايست كواليتي، لا، احنا بنتكلم على اننا فعلا بنحقق ده وفعلا فيجر اوت اللي احنا عايزينه بزيرو كاستمر كليمز. سريعا هنتكلم على الهوت شارج ابلكيشن. كنوع من السستينابيلتي حصل عندنا بيوفر حوالي 25% من الفيول كونسامشن، وبيديكريزنج السكيل فورميشن بنسبه حوالي 15%، وبيقلل الهاندلنج بروسيس بتاعتنا تقريبا ب 30% لانه بيتنقل عن طريق الكونفيورز دايركتلي من الميلت شوب الى ده فيلم بيوضح الشورت كات على الترانسفيرنج بتاع الهوت بيلت مباشره من الميلت شوب الى الرولينج ميل بغرض الاستفاده القصوى من التمبريتشر الموجوده وتقليل الويستج في الحراره. وده بيتم شحنه مباشرة الايتم الثاني الخاص بالكنترولينج في الريهيتنج فيرنس عن طريق عمل ثيرمال اوبتمايزيشن موديل باستخدام ليفل 2 سيستم. طبعا كلنا عارفين ان كل الريهيتنج فيرنس بيتم الكنترول فيه عن طريق ليفل 1، وده جميع المصانع بتقدم هذه الفاسيلتي، لكن الكنترول على ليفل 2 سيستم بيهيئ لنا بنسبه كبيره جدا الفول كنترول على الزونز وريكوردنج داتا بنقدر نتعامل معاها، بالاضافه ان بيبقى عندنا حاجه اللي هي كويك سيت اب للفرن نفسه، ان في حاله توقفات المصنع لفتره او توقفات طويله او قصيره بيتم التعامل معاها عن طريق بروجرامز بيتم وضعها، بما يؤدي الى كفاءه عمليات التسخين وفي نفس الوقت الحصول على افضل البروبرتيز للبرودكت بتاعنا. وبنحصل على ريبورتنج على كل فيرنس بارامترز، بالاضافه للفيرنس تراكنج اللي بيساعدنا على تراكنج لاي بيلت بدايه من دخولها الفرن حتى خروجها كمنتج نهائي 1 باي 1. دي طبعا بارامترز موجوده لكنترول الحرارات داخل الليفل 2 سيستم، ده البيلت تراكنج داخل الفرن، والريبورتنج اللي احنا بناخده من ليفل 2 سيستم. بالنسبه للكومبينيشن من الابرون سيستم مع التوين تشانل، احنا يمكن تقريبا المصنع الوحيد او عدد المصانع القليله جدا اللي موجوده في العالم اللي مطبقه الاثنين، وجود التوين تشانل مع الابرون سيستم. ده هنا كده بالنسبه لنا منطقه ال20 شانل بيتم دخولها على الخط، ودي منطقه الابرون، والاثنين كيبابل ان هم ينقلوا المنتج من خط الدرفله الى الكولينج بيد. وده بنستخدمه من المقاسات المختلفه، المقاسات الكبيره بنخليها على الابرون ميكانيزم، والصغيره على ال20 شانل. بيدينا يعني ادفانتج عاليه جدا في تقليل الويرنج ليميتس على ال20 شانل، مما يؤدي الى ان تاخد افضل جوده ممكنه للمنتج النهائي. و بيفيدنا برضو ان المقاسات الكبيره لما يتم درفلتها على الابرونز بنتفادى سقوطها من ال20 شانل، ما بيحصلش اي ديستورشنز ليها، وطبعا ليس مينتنس كوست على الابرونز. برضو كان في فكره ان احنا نشتغل مقاس ال 20 مللي، لانه سليتنج سايز احنا بنشتغل سليتنج من 12 مللي الى 20 مللي على 2 لاينز كلاترال، ادي 2 لاينز لاترال، وان احنا نشتغلوا على السنترال برضو عن طريق اديشنال كولينج بوكس بتساعدنا على ان احنا نستغنى عن استخدام التو فينشنج بلوك دول وندخلهم صيانات، فبنساعد على ان الكوست بتاعه المينتنس بتاعتهم تتحسن، وفي نفس الوقت في حاله اي ترابلز تكون موجوده نقدر ايزي ان احنا نشتغل على السنتر لاين بتاعهم. ودي صوره للسليتنج ال 20 ملم. الباركت اوبتمايزيشن سيستم، احنا بالطريقه الباركت اوبتمايزيشن سيستم بنقدر زي ما شايفين مجموعه البارات الموجوده هنا بيتم قطعها 1 باي 1 مع تحديد الطول اللي هيتم قطعه اوتوماتيكالي من كل بار، بغرض ان احنا نقلل الشورت بارز الموجوده، بنحسن اليلد بحوالي 3% وبنقلل الشورت بار باكثر من 60%. عشان كده بيبقى الكاستمرز بتوعنا نادرا ما حد منهم بيشتكي من اي اكزيستنس للشورت بار، بالاضافه ان بنقلل الهاندلنج بتاع الشورت بار في منطقه الفينشنج اريا. another advantage حطيناها في المصنع وبرضو من الحاجات اللي يعني الموديلز المحطوطه اللي هي الماجنت سيستم. الماجنت سيستم عباره عن ميكانيزم بيتم وضعه قبل الفاينل ستيج بتاعت الفاينل برودكت لان هو يشيل الشورت بارز الموجود عليه. ده بغرض ان احنا نتفادى تماما وجود اي شورت بارز في المنتج النهائي، لان احنا زي ما قلنا احنا اذا كنا بنسعى لزيرو كليمز لهايست كواليتي، فاحنا بنسعى ان ايفن شورت بارز كباند ما يكونش موجود حتى داخل الباندلز النهائيه. واحنا كده فعلا بنضمن الاكزيستنس، ما فيش اي شورت بار، وبنقلل المان باور النيد في الاريا دي، وبنسيفنج البرودكشن نتيجه السجريجيشن. من ضمن السستينابيلتي اللي احنا سعينا لها ان احنا اضفنا وحده للريفرس اوسموسيس سيستم للبلو داون ووتر، بحيث ان الميه اللي راجعه كلها من المصنع ما تعتبرش ويستج، لكن يعاد تدويرها عن طريق ار او يونت بحوالي نسبه ييلد حوالي 90%. والار او يونت دي قللت استهلاك الميه الميك اب ووتر بنسبه 33% وقللت الكوست بتاعتها 33%. وده نوع من السستينابيلتي اللي احنا بنسعى له بالذات في الميه نتيجه الشورتج الموجود في المملكه من الميه. و ايضا ان احنا بنحاول ان يكون زيرو ديسشارج بلو داون ووتر على اي شبكات. الايدنتيفيكيشن في السي بي ار ام هو طبعا باسم الراكحي، ونتيجه اللاينز الموجوده اللي احنا شفناها سواء اذا كانت واير رود او بار ميل او سليتنج او سنترال، فموضوع مجموعه من الماركينج بتؤهل ان اي واحد يقدر يتعرف فولي تريس لاي بار موجود عندنا. الحاجه الثانيه ان احنا الحمد لله فولي ابلايد للاي اس تي ام الديزيجنيشن سيستم الخاص بالسايزز. زي ما احنا شايفين احنا ده اوريدي ابلايد السايز، اوريدي ابلايد المواصفه، اوريدي ابلايد الجريد اوف ستيل، ايفن 60 or 75 لان احنا الحمد لله رب العالمين نجحنا في انتاج جريد 75 عندنا بكفاءه. فكنا تقريبا احنا من طليعه المصانع اللي طبقت الديزيجنيشن سيستم للبارز في المملكه هنا. الامبيشس اند ستاندرديزيشن بلان صراحه تم استقطاب مجموعه كبيره جدا من الشباب السعوديين، واتجهنا لتطبيق برامج ايفن اون سايت او اوت سايد في الخارج لرفع كفاءتهم والاستفاده بيهم والوصول بالتقنيه بتاعتهم لتشغيل الهايست تكنولوجي بلانت اللي موجود عندنا. ودي صور ليهم وهم في الخارج، وبنغطي بيهم اماكن حساسه جدا في عمليات التشغيل بالنسبه لنا، سواء التشغيل او الصيانه، وتابعوا معانا بدايات تركيب المصنع. والفيجرز بتاعتنا في الانجينيرز والمانجرز ليفل في السعوديزيشن حوالي 50% دلوقتي، و2% 32% من التكنيكال ستاف. وفي خطه طموحه بزيادتها 5% كل سنه، مع وضع سبيشال كارير باث للعماله السعوديه الموجوده لترقيه كفاءتها للسبيشال رانكس. الكواليتي ليفل عندنا زي ما احنا بنحطها كسلوجان بنعمل عليها، وعن طريق هايلي ستاف ممبرز ومع الايكويبمنت من المعامل الحديثه جدا، وبنطبق الابلاينج الاونلاين كواليتي سيستم. وده جزء مهم جدا، ان جميع افراد الانتاج مسؤولين عن الكواليتي وليس افراد الكواليتي بذاتهم، وده بيعمل خط الدفاع الاول عن اي ديفكت ممكن يطلع. والابلكيشن ده ادى معانا لان احنا نصل فعلا لزيرو كليمز ديفكت. بالنسبه للانفايرمنتال، وي ار نوت سكريفاينج الانفايرمنتال، بيتم بريوديكال تشيك عليها عن طريق كونسلتنتس موجودين معانا، وبيتم تسجيل هذه الميجرمنتس ومتابعتها مع الانفايرمنتال اوثوريتي، سواء اذا كانت البي ام 10 او النويز او الهيت ستريس في اماكن المصنع. النوكس ميجرمنتس المستخدمه بنقيسها بتجهيزات خاصه في المدخنه بتاعتنا، و يعني اقل بكتير جدا من اي نورمز موجوده في هذا الاتجاه. الاتشيفمنت اوف اور تارجت اوف زيرو كاستمر كليمز ده تم لاول مليون طن تم انتاجهم with zero claims من اي كاستمر. ده including الايرلي ستيج اوف بلانت كوميشننج اند ستارت اب، اللي نورمالي معروف انها بتكون هي فترات المشاكل الموجوده للفاينل برودكت، وغالبا بيكون فيها يعني ريزنج لبعض الكومنتس من الكاستمرز. لكن نحمد الله سبحانه وتعالى ان بانتاجنا مليون طن سينس ستارت اب زيرو برودكت كليمز، الحمد لله رب العالمين. طبعا ماكسمايزنج السعودي ستاف سكيلز زي ما اوضحنا، وزياده نسبتهم في الاورجنايزيشن، كومبلاينج لكل الانفايرمنتال ريجوليشنز اللي بتغطي البلانت اكتيفيتي بالنسبه لنا. شكرا. اتفضل لو يسمح الوقت. اسئله؟
Can we take some questions?
ألف شكر على الرائع البرزنتيشن الحلو، اتمنى لكم التوفيق ان شاء الله. تمام. بالنسبه للسيل الماتيريال بيس اون نمبر اوف بار اور بيس اكشوال ويت، فيها ممكن هذا ولا
سيلينج النمبر اوف
ماتيريال؟ يعني في البندلز لما تبيعوه على النمبر اوف بارس، على عدد البارات اللي فيه، ولا بالوزن؟
لا، نمبر اوف بارس.
نمبر اوف بارس. طب نمبر اوف بارس.
واعتقد كل المملكه كلها ماشيه بالنمبر اوف بارس.
شكرا.
شكرا دكتور احمد.
تمام. واحنا تقريبا زي ما تفضل الباشمهندس السيد، احنا انتاجنا طبقا للمواصفات الامريكيه بالتوليرانس بتاعتها ايفن بالوزن واليونت ويت بالاثنين، لان لازم تعمل كنترول على الاثنين، والا وزن البندل هيروح منك لو ما كانش accurate.
شكرا دكتور أحمد. الموضوع الهوت charging is really interesting. However, I have some question in this regard. What is your charging temperature?
الايم كان تقريبا 600 درجة، لكن الاكتوال وصل لحوالي 720 درجة.
Are we talking about hot charging or direct charging?
Direct hot charging.
Direct hot charging. How you synchronize the steel plant production with rolling mill production?
هو طبعا في we are trying we are in the early stage for commissioning of this hot charge system.
Okay.
So our plan is trying to reach for some sizes which is approximately complying the same capacity. Suppose that in the wire rod the sizes range of sizes is complying to our tonnage capacity from the melting shop. So by this one it could be applied even partially from the beginning and will be upgraded with time to fully comply.
What is the percentage of so far percentage of hot charging compared to the cold charging?
We are in the early stage of commissioning of this. It is not cannot be compared now.
Okay, thank you.
شكرا. Yes. We are using this now for the rebars.
For the rebars only?
Yes.
Okay.
Up till now.
And for the CHQ or the coal heading quality and for the electrode quality, you intend to do it later on?
We did not start this, and I think it can take some time for studying before applying.
I see. I saw during a presentation that you have used 130 by 130 billets as well as 150 by 150 side billets. Yeah. What would be the yield improvement from 130 to 130 using, say, case 1, 130 by 130 billets, case 2, 150 by 150 billets for producing same diameter of rebar, say 14 or 16 millimeter? What would be the approximate improvement in yield?
The approximate yield, approximately, we found this around 0.15. Approximately. 0.15.
Thank you.
Okay, welcome. Thank you very much. Yes.
Regarding the change in the size 13 and 15.
130 and 150, yes.
You said the improvement in the yield 0.1?
Maximum 0.15, yes.
Right. Is it worth really to have it? Because I think there is setup you have to make in the mill. You have to add something in the mill.
Yes.
So you did this modification, or you bought the mill, or the mill came with all this
yes.
stuff?
Actually, when we are changing from 130 to 150, it's coming by size. We are not shifting between these during the same size to avoid any discrepancy for the mill line itself. But sometimes we are obliged to use the both kinds of pellets on the same size. At this, we are utilizing the roll change time to adjust the gaps and run on. And by the way, we succeeded to operate this smoothly. We have no problem for that.
There is no addition for one stand or something?
No. It's already the same, but adjusting the gaps and adjusting the tension and adjusting all the mill line parameters.
What about the furnace? Once you said that you have the continuous change up from 130 to 150, one size. Was the furnace able to take the two sizes together? You have part of the furnace 130 and part of it 150, or you have to empty the furnace and then go for 150 size?
Actually, we succeeded to make this, but we did not prefer to have this, because if you are looking to the mechanism for the walking beam itself, it depends on the stroke, and we are trying to avoid any problems due to length of the billet for the furnace walking beam stroke itself. So we succeeded to run them together, but in reality we are keeping to run even 130 or 150. But the both cases already succeeded.
Okay.
Thank you very much. Thanks.
Special thanks to engineer أحمد همام مدير الدرفلة بشركة حديد الراجحي. الإخوة الكرام الآن ندعو الجميع لأداء الصلاة وتناول الغداء ثم نعاود استكمال أوراق العمل عند الساعة 1. Now we have a break for lunch and prayer and we'll be back at 1 o'clock. تكنيشنز انت ترى
اول ما اذا الاخوه طلعوا خلاص بس
انت اللي بتكون
لا نفس البرزنتيشن انا مش حديد الراجحي
يا انت اللي انت بتاخذ الحين يعني؟
اي لا بس هو ديليت بس انه حق حصر يعني
اتس اوكي كان دو ات ماذا كيف كانت؟
لا عادي اعرف بس انه قدام الحضور انه عادي يعني
خلص اذا كان شيء حصري فيه
Yes, but for the market also they are looking for the negative of the balance. So normally for the debarring coils, هيبهدلك جدا وانت تحدث السؤال. فاحنا كان عندنا توقع عرفت الحاجات دي مش موجوده عند اي حد. انا عارف ان كل
اي هو اللي طلع لي هذه المشكله. ايه اقول لك هو اللي خلاني يعني امس بعد بس ما فيها شيء. اوكي. لا كلمني قال شو اسمه كلمني قال شفت ترى هذاك خوالهم وزي كذا. انا حق ما ادري ما ادري الرجال حتى
ومنه بيرجع مفيش منه يرجع قبليه بواحد او اثنين.
هو في كذا حاجه لما يشتغل على البر الاخير لما يشتغل على البرات ده دليل اللي عندها الاثنين.
احنا بنشتغل على كله يعني ممكن يرجع معايا 3 4 برات.
يعني مش
شرط يشتغل على الدور الاخير اللي هو بيحطه كاساس، لكن منه بيرجع. طب هو قال اللي في المسجد ده بيقلد هو اللي او يبقى ما ياخدش اخر دور قصير عشان ماشي هو لكن هو ما بيعملش حاجه.
الاوفسايد كريشيو لان انت بقدر الامكان ما عندكش حاجه تطلع. لو انت المفروض عندك الميتابوليزم بيديك الالكول في 12 تمام، بيفتح لك الحته الزياده اكوردنج للكيوز عايز
مصنع كبير زي المصنع مصنع كبير زي مصنع
وكانت اول حاجه بنفكر فيها نجيب ويلدنج ماشين تمام، وبعد عملنا دراسات مستفيضه عن الموضوع ده لقينا ان الافكت بتاعها في الاخر ده اكشن يعني ما كانش بالصوره اللي حد يتخيل. احنا محققين ليست عاليه قوي.
لا اصل انا اشتغلت على
هي بتحقق، لكن فعلا احنا بعد دراساتنا مع السبلايرز
ده اقل حاجه
والله احنا الدراسات مع السبلايرز والبيبرز موجوده ما اديتهاش الافكت اللي بيوازي مع التايمنج.
العائد منها
العائد منها مع التايمنج اللي ممكن تاخده او كده مع الديستنس اللي احنا نحطه ليها، كل ده لقينا ان احنا افضل شغل محققين اللي احنا عايزينه. ما هي موجوده شغاله بنتكلم عليها 200 طن في الساعه، رقم كبير جدا. التايم جاست
يعني التايم
بيأثر معاك. كل المصانع وكل الدنيا كلها شغاله وكل البنايات اللي قدامك كلها على السي. بس هو وزاره التجاره وزاره التجاره وزاره الاسكان كله مرتبط بالخدمات المستشفى. لا خايف انت موجود في وزاره التجاره غير مقام ومصنع لكن غير مقام ومصنع التجاره قدر بتغني نظام ورشه التجاره. لو حطيت ليبل يروح لليبل مصر. لا 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 هو اقل نقطه غير مسؤول لان ما جبناش عينات منزله عندنا 54 75 930 لكن 74 ناجحه الثاني ده فاشل ازاي زي ما انت حلت المشكله لو حلت المشكله دي ان شاء الله تحل هو هو عارف مش كل ده بس لجان ومش لجان ماشي هو واحنا اعتقد انا الوقت هذه لازم تفرض راي اجتماعي مع المصانع هذا لازم يكون مطبق يكون اجتماع بعد هذه الورشه وبالعكس دوريه فيها محاوله ان شاء الله بالتوفيق احنا جينا ركبنا المصنع جاب بزنس كارد طيب ماشي اوكي بص سكشن 20 ده المنتج النهائي لا مش 20 ده السكوير بص في كراكس الله بركاته ثانك يو ثانك يو ثانك يو ثانك يو استعمال الوصول والمنتج النهائي يطلع كويس. ممكن يدخل فيه حاجه بس مصيبه كتير مع البطل. ده عندنا كام بطل بطل؟ 8 عندنا راجل عندنا راجل 7 بطل. قدت يعني يعني كام واحد الله يخليك.
مقترحات روح كده أصلا.
Oh, 5 seconds.
بسم الله. نجدد الترحيب بكم حضورنا الكرام في هذه الورشة تحت عنوان تصميم السبائك المقاومة والممطولية. الجزء الأول هي ورقة العمل 11 لهذه الورشة، يستعرضها الخبير الأمريكي روبرت جودويسكي، فليتفضل. On behalf of you, I would like to welcome him to the stage.
Thank you, and welcome back for the afternoon, and I guess the last session. I don't know what my schedule is. But how much time do I have? This one? Yeah. No, I just don't like it for this. But no breaks. We don't need a break. I think a break is a good idea. Yeah. Then it's all right. Yeah. I've got 4 items. Hopefully, I probably won't be able to get them all in, so I'm making a priority list right now. It isn't necessarily going to be what's on the schedule, but it's things that I have that I think are important. I'm going to start with the first one with number 6, if the translator wants to refer to that particular set of slides, number 6. I think this subject is fairly important, that we've kind of realized as we're coming here, and this specifically for the rebar situation we've been discussing, it is the retest, the bending retest, because that all the specifications in ISO, as we referred to, and SASO require the 100-degree C, or the boiling water, age for an hour, give or take, between the bend and the rebend. And 100 degrees C for an hour on a strained steel specimen is the ideal temperature to test for nitrogen strain aging. Well, nitrogen strain aging is also a very important mechanism to control if you're into the wire drawing business, particularly high carbon wire drawing business, which is what I did for quite a few years in my previous life. And so had done a little background work. So I thought I would share that work with you so you can kind of understand some of the basic concepts of nitrogen strain aging, what's important and isn't. And because I'm not quite sure yet what to do with it relative to this testing, but it kind of gives us an all perspective of this is the mechanism, the animal, if you will, that we're all working with. And so we need to understand it. So if we take it anywhere from here, we'll know what we're dealing with. So I can show you the information I have, and hopefully it'll be useful. Okay, oh, yeah. I'm going back to this because I wanted to kind of apologize, because yesterday I was talking about, and I was comparing specifications, and I only used this table 1 to represent the SASO chemistry requirements. I didn't note that 2 paragraphs down there was also this other requirement that I passed over. I didn't realize. And of course, for carbon, it's like, well, it's in between. It's not really significant. It's just a value that's in the same range as what we were talking about. And the sulfur and the phos, according to this, it's a bit more lenient than what was there in the table anyway. I'm quite sure what the intent is. And also it says the percentage of each of carbon, sulfur, phosphorus, and nitrogen weldable bars shall not exceed the following. But yet you don't have a weldable bar classification or identification, so how does one know when he orders to the SASO spec whether or not he's getting a weldable bar? Those are, maybe you guys have the answers to that. I don't. But the reason I have this up here is because of that last line. There is a nitrogen requirement in the weldable portion of the SASO spec. I didn't realize that yesterday in my discussion. Somebody was pointing it out. It might have been you. Yeah. Yeah, for the hot rolled high tensile rebar. Yeah. Yep. But most international specs are 25. For weldable grades. A lot of them are. Chinese, for example, are 25 carbon even. So, yeah, and what is the important carbon and the carbon equivalent? I agree with you. It does boil down to cost because carbon is by far the cheapest of the alloys that you have available to you. Yes. Yes. Yeah. Okay. Some questions that come with that are, number one is, how do I know when I order a SASO spec that I'm getting or not getting a weldable bar? And how do I order it? Because you don't have, I didn't see any designation in there. You have the 3 types of bars, but you don't have a, quote, weldable version of it defined. But suddenly there's this chemistry requirement for welding. Yes. There is a marking for it? Okay. And I did. Okay. There we go. Hopefully you'll hear me better now. Okay, so there is a marking, so there at least, so there's got to be a provision for ordering and all that stuff. Well, good. Of course, the next question is what effect does nitrogen level have on weldability? It's frankly, when you go back to most weldable specs, I don't really see nitrogen content as something that really determines weldability. I've gone to places like the Edison Welding Institute and TWI in the UK and asked the question, you know, what's the negative impact of me having nitrogen in there? And there is very little. But it is in here, so I'll simply just raise a question. I'm not going to deal with that. But what I will deal with is how nitrogen content can impact our ability to meet the rebend test. That's really what this is about. So there is 130 ppm maximum in the weldable version of the SASO spec for rebar, and there is no provision for tying that nitrogen up with a microalloy that I know of. Do you agree with that? There is no footnote like there is in ISO that says that 130 max does not hold if you have tight nitrogen binding elements. That does not exist in the SASO spec. So, even if we did that. But let's look at nitrogen in steel, and of course the historical perspective is nitrogen's always been identified as an undesirable element in steel. Often nitrogen is targeted for reduction or elimination by advanced steelmaking techniques, particularly true in the wire drawing industry. Current situation is that electric arc furnace steelmaking is continually increasing. And as an example, in the U.S., it's over 50% of the total steel production. And steel, rebar, and rod production is over 90% EAF in the U.S. In fact, I don't know of any rebar that's not electric arc furnace. Most of the wire rod is electric arc furnace. So wire drawers and rebar producers have to deal with this higher nitrogen level. And we know that when uncombined nitrogen exists as an interstitial or free nitrogen in ferrite, really much the same as carbon. It's carbon and nitrogen are very similar in their performance as an alloy or as an interstitial alloy in steel. Free nitrogen can actually be used as a strengthener. The strengthening component of free nitrogen in ferrite is fairly strong, about 5 megapascals for every 10 ppm addition of free nitrogen in terms of strength level. The disadvantage of nitrogen is that it can contribute to reduced ductility through a strain aging mechanism where dislocations are tied up by nitrogen atoms, Cottrell atmospheres, if you will. In rebar testing, artificial aging at 100 degrees C and rebending after initial bending maximizes the possibility of nitrogen strain aging effects. As I said earlier, 100 degrees C is nitrogen aging, 200 degrees C is carbon aging. If you age at 200, you'll get about the same amount of aging, whether it's carbon or nitrogen. But at 100, you do not get carbon aging, but you do get nitrogen aging. So it seems the rebend test is specifically designed to test for nitrogen, free nitrogen. But going back to the beneficial effects of nitrogen, I mean, it is a useful for nitride forming elements like aluminum and vanadium and titanium for things like austenite grain growth control. And in fact, they're very dependent on it. Aluminum would not be a grain refiner if you didn't have nitrogen in the steel. It does not form a carbide. The only precipitate aluminum forms in the steel that allows you to use it as a grain refiner is nitrogen. And it's also, I always like to comment that a lot of people say O2O aluminum will give you fine grain steel. And I say, no, it won't. Not without at least 50 ppm nitrogen. If you don't have the nitrogen, the aluminum will not provide you fine grain response. Yeah, you have to have a nitride. And have you ever seen a specification for fine grain steel that has a minimum aluminum and a minimum nitrogen? You will never see it. But yet, it's absolutely required. It's presumed, but it's not measured or required. With vanadium, the nitrogen-rich carbonitrides are also the most effective form of precipitates for strength, and you'll probably hear that a number of times this afternoon as I go through my presentations. However, aluminum nitride and titanium nitride and even nitrogen-rich niobium carbonitrides, to some degree, do not effectively provide precipitation strengthening. The nitrogen-rich niobium carbonitrides tend to precipitate in the austenite rather than the ferrite, and in order to get strength, as we'll talk about later, from precipitation in a ferritic steel, it has to precipitate in the ferrite, or at least during the transformation. Well, how do we measure the free nitrogen? Well, there's chemical analysis techniques, there's internal friction testing, or you can use a strain aging index, which was proposed by Baird about 60, 70 years ago now, probably. But basically involves uniform pre-strain of a tensile sample. It can be anywhere from 3 to 10%, but it should be well within the normal uniform strain hardening range. And then you age it for this 100 degrees C for 1 to 4 hours. And as we said, 100 degrees C is considered below carbon aging temperature. Then you retest in tension, measuring the flow stress increase from before and after that aging step. Any increase in flow stress, therefore, is due to this aging and is called the strain aging index. And what that looks like graphically, yeah. Not a big effect. And even I think in many cases the toughness issue that you're talking about is not directly nitrogen, it's probably indirectly relative to what it's doing with the other elements that are there and how people tested it. So while I'm not saying it's not true, there's more to it than just nitrogen. But that depends on the situation and the analysis and so on. But certainly your statement is true from the perception standpoint. People believe nitrogen is negative and certainly can have, under the right set of circumstances, a negative impact on toughness. And so that is true. This is the Baird technique for determining what we call an aging index. And as you can see, it's this delta. The aging index is this delta Y, which is simply saying take a sample of steel, and this could be the rebar. You go through the yield point elongation into the uniform strain hardening portion of the curve, and you simply stop the test and let the load drop off. And then you age it. You take that sample out and you age it in boiling water for an hour, 2 hours, and then you bring it back and you reload it. So you're in essence loading back up the same elastic line that you unloaded. And the question is how much increase do you get in the stress required to get the flow going again compared to where you were? If there's no strain aging index or no age hardening or no nitrogen in the steel, that will just continue on up this lower flow stress like you never stopped. But if it goes up higher than that, obviously something has happened. And that's called aging. That's the aging index. And the amount that it increases is the quantitative measurement of aging index. So that's a quantitative way to measure, in essence, the effect of free nitrogen in your steel. And it tells you, because measuring actual free nitrogen in the steel directly chemically is a very difficult thing to do. Because all the tests for nitrogen to give you total nitrogen, not free nitrogen. So when, again, you look at some of this, here's some Morrison's report using this very technique for measuring the aging response, aging index, versus the free nitrogen content, at least as he determined it. And you can see there's a pretty well-defined curve there. And some of the interesting things is it tends to max out at a fairly low level, maybe 60 ppm. And above that, you don't get any more. You maximize out the amount of strain aging index you can measure at a relatively low level of nitrogen. So simply saying, well, if I want to minimize my aging index, I want to keep it, say, below 20 or 15 or something like that, I'm going to have to ask for some pretty low nitrogen levels, in fact, levels that are pretty impossible with today's steelmaking techniques. Here's another Wilson and Gladman, another famous researchers looking at the same problem, more or less, looking at aging, and here trying to sort out the difference between carbon aging and nitrogen aging. Again, the uniqueness is, now they didn't push, whoops, the nitrogen content very high, the free nitrogen content, because they only go up about 15 or 20 ppm, but they're already up to this 50 or 60 level of aging index, which it turns out is about as high as you can measure. So it doesn't take a lot of nitrogen, and again, there's some disagreement or discrepancy between these two approaches as to how much that is, but it's a relatively low level of free nitrogen will give you totally maxing out the effect of free nitrogen, at least based on the aging index indicator. Yep. They believe they separated it. There was some recent work that I was going to have presented, but I don't have it available. Some recent work done at Colorado School of Mines at ASPPRC on that very subject. And it was amazing how clearly it said, because they were looking at steels, comparing carbon only. I mean, they had titanium, they put titanium in it, they had basically no free nitrogen versus a fairly high free nitrogen, and they tested it. And at 100 degrees C, they got no carbon aging no aging at all in the one with no free nitrogen, but they got full aging in the one with free nitrogen. And they go to 200 degrees C, and then you couldn't tell the difference between the two of them. So they were both at the same level. So the one that had no nitrogen, the carbon aging was just as strong and got just as good as a result, but you didn't see any of it at 100 degrees C, but you saw a full impact of it at 200. That was the most clear evidence I saw of this distinction between those temperatures that I've seen in a long time. I don't think they published that. That information is available. So yeah, I feel pretty confident that you can separate out carbon aging from nitrogen aging simply by this temperature differentiation. So, conclusions, I probably already said them, but I'll repeat them here. Significant strain aging occurs even when the nitrogen level is as low as 20 ppm. So in other words, if you're going to designate something to have no strain aging index, you've pretty much got to get rid of all the free nitrogen. Over 60 ppm, additional free nitrogen doesn't really change that index any. So it starts to raise a question, above 60, what difference does it make? And yet our maximums are twice that, 120, 130. But it says I get the same effect of 60 as I do 120. So how does staying below 120 help me? That's a rhetorical question. I'm not sure there's an answer. The reality is we know that in many real-life situations, there's a distinguishable difference between 60 ppm and 120 ppm free nitrogen. Wire drawing, we can easily see that. Can we see it in the bend and rebend test? I'm not sure, because the fact that you're doing 100-degree aging for an hour says I'm maximizing all the strain aging and nitrogen strain aging I can get, so it doesn't take very much to give me the negative effect. The question is the reband test as severe as the aging index test? In other words, will it respond to the same degree of aging? I don't really know the answer to that one, but I do know that the 100-degree CH for an hour that's really maximizing. That's saying any free nitrogen I got in there is going to contribute to strain aging. And it doesn't take a lot to cause a problem. Certainly it doesn't take 120. It may not even take 60 ppm. So this 0.012 or 0.013 max nitrogen, what's the value of it if it's going to strain age with 60 ppm nitrogen? Well, yeah, that measured, but the presumption is it's totally available. Because if you're saying I'm only doing the free nitrogen, you have no idea what that is. You have no way. So you can only do the total and assume that's what they expect the free nitrogen to be. That's with no nitrogen binding elements added, which, of course, isn't always the case. And we will talk about that here in a minute. Of course, this all suggests, I think as I probably said, that it is impossible to eliminate nitrogen strain aging in steels simply by limiting the nitrogen levels. Even today's best steelmaking procedures cannot keep nitrogen levels below 20 ppm. That's an unrealistic expectation. So the only alternative to reducing the nitrogen level, the free nitrogen level, to those numbers or lower, is to add other nitrogen combining elements. Yet an extensive production experience of high carbon wire, referring back to that, has shown that reductions of nitrogen levels at higher equivalent levels, for example, the 60-week high carbon wire rod, we can tell the difference in performance between a wire rod with 80 ppm nitrogen and 110 ppm nitrogen. There's a big difference in response. But we're talking about a wire drawing application where the aging is not optimized. In other words, you're not really doing 100 degrees C for an hour, you're doing maybe 120 degrees for a second. And so, okay, it may be that if you only do the partial aging step, a limited amount of it, that a higher degree of higher percentage or content of free nitrogen will give you more of a problem quicker. But eventually it will all be bad. At least that's my way of rationalizing this. So we know, practically speaking, that there is a difference in steel between as you go up to, so I say that there's no difference between 120 and 60, yet I know there is. There is no difference based on the aging index study, but in reality, there still is some differences. These observations are based on wire ductility tests, torsion tests, rather than strain aging. It's simply a response to wire drawing aging. Quantifying the effect of free nitrogen on rebend testing in rebar would be important. I'm not sure that's ever been done. It seems to be the logical thing to do. If this is what you're doing and that's a test requirement, where's the data that says there is that link and what is it quantified? Something somebody maybe ought to do. And is the rebend test the way to evaluate it? Because it's probably, looking at cracking on a rebend test is also a function of other things like surface quality and a few other issues that you might bring up. So it's not directly measuring the embrittlement of the steel itself. Certainly it's part of it, but it's not all of it. Yeah, you can overage it and it can go away, but typically it's not going to do it at ambient temperature. It will eventually age to that point at ambient temperature, but it's probably not going to overage to the point where you lose it all. But if you heat it to, maybe 500 or 600 C, it will go away. Yeah. So, and this is stating what I already said, the much shorter time at high temperatures during wire drawing perhaps reduces the distance nitrogen can diffuse to locations, and that higher nitrogen levels provide more nitrogen available for local sites. And so you do get this greater degree of strain aging susceptibility, strain aging potential with higher nitrogen contents for less than optimum aging conditions. A reduction of free nitrogen, either from decreasing total nitrogen or tying up free nitrogen from nitrogen-binding elements, would then be beneficial for reducing the susceptibility to nitrogen strain aging during wire drawing. The point there is that you don't necessarily have to have a stoichiometric amount of nitrogen-binding elements to get a positive effect. Simply tying up some of the nitrogen is likely to be beneficial. The bend and rebend testing, while maximizing the aging effect by artificially holding at 100 degrees C for an hour, may not be as sensitive to free nitrogen as the aging index test. But again, don't know, because don't really know the characteristics of the failure modes involved and what level of embrittlement you really need to fail or not fail this test. Just, it's somehow that's what you're testing, but it's pretty hard to quantify anything other than a break or no break. And then that break isn't always going to be always from the same set of conditions. It is likely then that tying up only some of the free nitrogen with a nitrogen binding element would be beneficial even as rebend testing. But we don't know that. As far as we know, it hasn't been quantified. But I suspect it is, because I don't think if 20 ppm nitrogen gives you close to a full strain aging index, 20 ppm of free nitrogen is not going to necessarily cause guarantee a failure in a rebend test, because we know just about every rebar made's got at least that much free nitrogen in it. So there is some higher level of nitrogen that becomes the threshold value, but we don't know what that is and why. Some people threw some numbers out, and the reason the 120 and 130 numbers come out is because those are the numbers the steel makers say, I can live with that. That's the only reason those numbers are there, not because they're quantified as being a critical level for any mechanical or aging response. Free would be atomic form. It's assumed to be atomic.
Applied in the weldable bar. This is my opinion about this.
Okay. Didn't follow that, sorry.
In the British, it's a weldable bar. Then this is applied the ribbon test.
Which test?
Ribbon test.
Okay.
Then the ribbon test is okay to the applied on the weldable bar.
So we're saying most of the requirements in the SASO for nitrogen came from the BS standard. I have to read the BS standard to understand that. I haven't done that. I'm sorry. So, yeah.
nitrogen 120 max, ppm max, should be applicable. Because for this weldable, they will rebend, and therefore the free nitrogen which is there will come out in the rebend tests. But then how does the nitrogen affect the weldability?
I ask. Yep. Yeah, I don't know why, because I spent the last 15 years telling steel makers to add nitrogen to their steel. And I've been very successful at it, under the right set of conditions, of course. And in 15 years, I have not had one single complaint from anywhere in the world that said because that nitrogen level went up, they couldn't weld it or had any semblance of a welding problem. I've gone to Edison Welding Institute and say, can you envision there being any problem? And they said, no, carbon is much worse. But there's never a serious concern about carbon. There's a carbon equivalent, yes, and a max carbon, much higher in content than this nitrogen that we're worried about. And I'm going, what's the problem? And nobody can put their finger on it or tell me. So I'm going on selling this product under presumption there is no problem, and I have yet to be proven otherwise. So that's why I can stand up here and say that, is that show me the problem, and nobody has done it. Okay. We could, yeah. Does free nitrogen contribute to surface defects? What free nitrogen does, well, in this case, we don't need to talk about free nitrogen. We can talk about total nitrogen, because what you're talking about is the total gas activity in the liquid steel at the point of solidification, which is typically at the skin of the caster in the mold. And what you're talking about there is total gases. And nitrogen is one of the gases that contributes to total gases, that if those total combined number exceeds some critical value, then you will start forming blowholes, and blowholes then can form pockets in the surface that end up as seams when you roll it. And the answer to that is yes. But there are three gases that contribute to this: hydrogen, carbon monoxide, it's really oxygen, but it's in the form of carbon monoxide when it causes a problem, and nitrogen. And of those three, nitrogen is the least of concern. It's about 80 to 1. Hydrogen is 80 to 1, 80 times more critical than nitrogen. And so when people talk about that and talk about these seams, you find out it's really hydrogen that causes a problem, because it's the uncontrollable element. Nitrogen, you know what it is. Oxygen, you know what it is. Hydrogen, you don't know what it is. And when you suddenly have a problem, it's almost always because the hydrogen is spiked. Now, does the difference between 50 ppm and 150 ppm nitrogen raise the threshold of what a critical hydrogen level would be? And the problem is, the answer is probably yeah, it is. That you need to be more careful when you're operating to a higher nitrogen level than a lower nitrogen level. But it's not the nitrogen that really created the problem at the end of the day. It just set up the system to be more sensitive to hydrogen. So, yeah, I've had that question before.
You speak about the relation between the increase of can you give the equation between the increase of nitrogen and the increase of tensile?
There's a couple of papers that have been published in AIS Tech about 3 or 4 years ago. I have them in my computer. I'd have to look them up. Sunday Abram from Evers, Regina at the time, he's elsewhere now, but wrote a paper on that. And he did try to quantify that with equation, because they actually they used that equation at their caster to predict breakout potential. So in that, they came up with a a relative equation of the severity of the nitrogen, the oxygen, and the hydrogen. Hydrogen, again, being by far. That's where I got this 80-to-1, because I remember that from that paper. And so it's been attempted, empirically done, for sure. Change me out. So all those questions are good, and they're that's what comes when I get into this discussion. What about this and what about that? So please keep them coming. I haven't heard one I haven't heard before yet. Yeah, and here we said that even a partial tying up of free nitrogen, if in fact may help you with the bend test. I question whether it makes any difference in weldability, but we've discussed that. Okay, so then if you're going to tie up some nitrogen, what do you tie it up with? What are your choices? So let's walk through those choices, what the impact of each one are. The first one, of course, the one that everybody thinks of, as we've discussed to some extent already, is aluminum. Aluminum is added to many flat-rolled products virtually universally. But they can do that because they use submerged nozzles and powder cast. They don't have, and stopper rod blockage, so they don't, if they get a little blockage in their steel casting process, they can break it loose and get it going. So they've learned how to live with aluminum, so they use aluminum all the time. But I guess we'll get into the details. We'll list those elements that are available. Aluminum, titanium, niobium, boron, vanadium. Those are the 5 that I will discuss. I don't have moly in there. I know there's some moly people up here that like moly, but moly doesn't tie up nitrogen, so that won't help you there. Aluminum is not available for most rebar producers. Their casting process won't allow them to do it. It doesn't really precipitate as aluminum nitride on cooling anyway. Virtually all hot rolled products that have aluminum in it do not benefit from the presence of aluminum relative to their grain size. And if you've read my papers from AIS Tech on that subject, if you haven't, please do. But aluminum is totally useless, irrelevant, relative to grain size control in an as-rolled product. And the reason is it doesn't form aluminum nitride on a continuous cooling curve at cooling rates equivalent to most commercial processing routings. It just doesn't precipitate. It's too, even though thermodynamically you would expect it, kinetically it doesn't happen. It only happens on reheat. It doesn't strengthen, the aluminum nitride doesn't strengthen the steel, but it doesn't lower it. I've had interesting discussions with people about, well, does the aluminum nitride precipitate strengthen the steel? And the answer is they say no, but the flip side is the removal of interstitial nitrogen will weaken the steel. But yet when you add aluminum, you get virtually no effect. So then the presumption is maybe you're getting just enough precipitation strengthening from aluminum nitride that compensates for the loss of interstitial nitrogen. And you end up with a net zero at strength. But it can be an effective nitrogen getter and an austenite grain refiner if you have subsequent heat treatment processes in the steel making thing. But a rebar is not heat treated. So aluminum will never be of any benefit to you in reducing strain aging in the bend-rebend test by reducing free nitrogen level. Titanium can cause extreme difficulty during open stream billet casting. I would say we have done it. We had products that we actually did it, used titanium, but it had its negative side effects, for sure, because it forms oxide scum on the surface of the mold, the steel in the mold, causes surface defects, causes a number of things. But you can cast it, but it creates difficulties. But it's very effective in tying up nitrogen. And it will actually precipitate, even start precipitating in the liquid, and very quickly after solidification. If you have excess titanium, it will start to form sulfides and carbides. In fact, be a very effective strengthener as titanium carbide, but only after it's eliminated all the nitrogen and sulfur. Only titanium carbides strengthen the steel. Titanium nitrides do not strengthen because they're much too coarse. The large non-deformable titanium nitride precipitates, which can form, are detrimental for wire drawing applications. Again, this is originally written for those applications, so you don't want titanium in wire. But they can be effective, these titanium nitrides, particularly if you're hyperstoichiometric in nitrogen. That means having more nitrogen than the stoichiometric ratio with titanium. In other words, keep the titanium level addition very small. Then they can be effective grain refiner, and it does tie up free nitrogen. So, to some degree, a small amount of titanium addition to rebar might be useful if it doesn't cause you too many problems during the casting process, but it doesn't add any strength. And it can control grain growth during the rolling process to some degree, whether that, we're talking austenite grain growth in that case, whether that eventually contributes to a finer ferrite grain and a higher strength in the rolled rebar is a bit of a question mark. But it is something that will tie up a little bit of nitrogen. But the titanium nitride itself is not a strengthener. The next one is niobium. In this case, the stoichiometric ratio of niobium nitride is 6.6 to 1. In weight percent, it means you would need 0.6 niobium or greater to tie up 100 ppm nitrogen. It's a lot of niobium. And not all of that niobium is going to go to nitrogen. It's going to form carbides, particularly at these carbon levels in the austenite. Niobium carbide has a similar solubility, and carbon is present at much higher levels than the nitrogen. So therefore, you're going to get more niobium carbide precipitate than you are nitrate. And also, it's been well documented that you can get some very large precipitates, niobium carbonitride precipitates in these steels at this carbon level in these higher carbons that just don't dissolve in the rolling mill operation. And dissolved niobium will strengthen as niobium carbonitride and ferrite, but only 0.01% niobium will be dissolved in a 40 carbon steel during billet reheating to 1180 C. So it's a very small amount of niobium you can actually get into solution to form a precipitate on cooling. And remember, all precipitation strengthening, you have to have the microalloy in solution in the prior reheat and have it precipitate in the ferrite during and after transformation in order to get that strength. And niobium is very difficult. Now that doesn't mean you can't get a little kick in strength from a little niobium addition, but don't presume it's going to effectively tie up free nitrogen for you. No, it's really more an austenite conditioning thing. I don't see it as a solution strengthener to any great extent, particularly at this low level. It's see, from precipitate in a normal reheat operation for rolling, like rolling rebar, heated to 1200 C. If you look at the solubility of niobium carbide at 40 carbon, it's very low. It's the rest of it, because there's plenty of carbon available, because it's all austenite now where it's fully dissolved, you're going to have niobium carbides all over the place in the austenite, but not but you won't dissolve it, so it doesn't contribute to strength after you roll it. Yeah, they can grow large. If they exist in the reheat temperature, they will grow to be too large to be a precipitation strengthener. Yeah. Go talk to your niobium supplier. He will tell you, keep the carbon down and the nitrogen so you can keep the niobium in solution. Very good. Yeah.
Rolling temperature should be this one.
And this is an example. I'm not saying that's what it needs to be. I'm just saying at that temperature, you can only get that much niobium in solution. Typically, you probably should be a little higher than that. But that was just a number I picked as an example. I just plugged it into the equation. There is no right temperature. It's just each temperature has its own solubility. You just put it in the... No, what I'm saying is that at 40 carbon, the solubility for niobium in the steel at a reheat temperature like 1180, but you could do 1150, you could do 1250, and do the calculation, you will find you can only get a very small amount of niobium in solution, typically less than O2. So adding any more than that simply creates more precipitates in the inclusions in the austenite. Okay, I didn't hear the question, but it is dependent on carbon. The lower the carbon level, as you said, then you can get more niobium in solution and you make more effective use of it. Boron. Boron is probably not something we're going to be adding to rebar just yet, but boron is a very effective nitrogen getter. And it's particularly unique as it's the only nitrogen getter I know of that lowers the strength. So it's very useful in low carbon steel. And it's in essence what we call the poor man's IF steel. To finish, okay. Whatever. We had till 3 on the schedule. That's what I was presuming.
What you are doing now, this part.
Okay, you want to take a break?
We need a break.
Okay. Okay. When we get done with this one, we will. All right. I've got a lot of. I will have more things to go over, and we'll have time for. So, yeah. But I want to hit. We'll assume that I want to hit what we are talking about quite effectively. Boron is unique because it lowers the strength. It's useful in low carbon steels, whether they're sheet or low carbon wire rod. Our basic 1006 wire rod. It replaced rim steel rods at the low carbon because of its high ductility. It's really interesting what boron can do, but it's not relevant to rebar. So we'll get to the one that is relevant to rebar, and that's vanadium. It's the most widely used microalloy for rebar, and it's very effective at tying up nitrogen. It prefers nitrogen over carbon, so effectively ties up nitrogen even in higher carbon grades by interphase precipitation or precipitation in the ferrite. Consistent and proportional strengthening with this vanadium addition. Can be dissolved during billet reheating, even at high carbon grades, minimizing any large precipitates. So vanadium, at the end of the day, that is your ideal nitrogen getter for a rebar application. And it's also your ideal microalloy for strengthening. We'll get to that later. But to show the strain aging things, we did some, I did some strain aging studies. In this case, again, we were looking at wire applications, so there was some 1080 work. base chemistry of 80 carbon, 70 manganese, 28 silicon, normal electric furnace resid metallics, and we varied the vanadium from 0 to 0.9, and nitrogen levels from 006 to 023, and we did the strain aging index with a 3% pre-strain. We're using a small pre-strain because it's a high carbon material with a relatively short uniform elongation range. We did this in the as-rolled conditions, starting as-rolled condition. We did a 4-hour aging at 100 degrees C in this case to make sure we completed all the aging. And this is what that curve looked like. And looking at the axis down below, it is the VN ratio we're looking at there, not just nitrogen content. And of course, stoichiometrically, vanadium to nitrogen, 3.6, 3.7, so almost 4. So bottom line is, once you got above 4 in the vanadium to nitrogen ratio, your strain aging index was less than 20 megapascals, and that suggested the free nitrogen content was less than 20 ppm, regardless of nitrogen content. And as you can see, it was all over the map. Here was an 023 nitrogen, 230 ppm nitrogen with enough vanadium to do a 4-to-1 ratio, only 20 ppm strain aging, which is like almost nothing. So, okay, are you going to tell me that's a product you can't use in rebar because of strain aging when it doesn't have any, even at 230 ppm nitrogen? So, you know, that's the kind of problem you run into. It's not the total nitrogen content, it's the free nitrogen, and the free nitrogen's depending on a lot of things that you're not even taking into consideration. So, yeah, it is nitrogen ratio really defines, vanadium nitrogen ratio above 4 says I ran out of nitrogen. Below that, I have free nitrogen. I get strain aging index if I'm below that. Here's some production 1080 rods. This wasn't lab heats, this is production heats. Again, 80 carbon, 70 manganese, 035 to 45 vanadium added, various nitrogen level, and the strain aging index was studied. 3% pre-strain again, same aging index, and we get results like this. And basically what we're comparing here is some production heats with more or less, the same vanadium and nitrogen content, so they all kind of scatter down here. But as you can see, a standard 03 vanadium addition virtually eliminated strain aging index. You can take the same material, or in this case a niobium material, and the other were plain carbon, with the same nitrogen level, but no vanadium, okay. They have 60 to 80 megapascal strain aging index, which is about the highest you can get. So I would say the vanadium was pretty effective at eliminating strain aging, regardless of the nitrogen content. If you look at, we also look at strengthening. This is just looking at the lab melted same heats, looking at strength increase, and we came up about 5 megapascals for every 10 ppm nitrogen. Which is about what we normally expect to see, and data looked like that. So not only did we tie up all the nitrogen, we got strength, and predictable strength. Here were this is some work we did on low carbon 1006 flat rolled sheet material. Again, strain aging index, looking at various chemistries, but it's basically a 1006 with variable amounts of silicon, manganese, aluminum, and vanadium from 0 to 0.13, nitrogen from 70 to 200 ppm. Low, it's metallic, it is an EAF product, but with low coppers, 10 max copper. Strain aging index 7.5. What we did in the as-rolled conditions, we found, well, there's a lot of scatter in this data, but this data was done, the samples were taken right after actually before the downcoiler, and cooled quickly without enough time to allow the full precipitation of vanadium nitride. So what we did, we simulated coil cooling, which every coil would normally go to, reheated them to 600 degrees C and then furnace cooled, as you would, and then retested the strain aging index. And there's where we got, okay, no strain aging for VN ratios of 3 or higher after simulating the coil cooling. So you do have to have some time for this precipitation to occur, but this occurs after the austenite to ferrite transformation, typically in the 600 degree range. And that, but you get enough of that in most bar cooling situations. What it would do in a QST is kind of interesting, which is kind of another subject, and I still think it could be effective, but it's a study needs to be done on its own as well. But in the as-roll condition, we've seen that's very effective. So conclusion, strain aging susceptibility cannot be predicted from total nitrogen levels alone. For complete static strain aging, the maximum aging index can be achieved with as little as 60 ppm free nitrogen. Higher nitrogen levels potentially increase the probability of aging for a given wire drawing practice, and therefore potentially for the bend and rebend test. For marginal wire drawing situations, even a partial reduction of free nitrogen is effective, beneficial, at least. Of the common nitride formers used, only boron with lower strength. Of the common nitride formers used, vanadium offers the best properties for increasing the yield strength of the bars. And to optimize the strengthening effect of vanadium additions and reduce strain aging, sufficient time must be available after ferrite transformation to complete the precipitation process. So that's what we learned from that study. So that's the next one. We will take a break now. Good time for a break. I've got a number of other things to give you. We'll run out of time first. Oh, okay. I get a drink of water. I guess that's available. That's somebody's, I don't know. Yeah.
You gave me has included all this?
Yes.
All of it. السلام عليكم. الحقيقة يعني
And all the papers it came from.
قبل ما أتكلم عن الموضوع الآن المفترض إنه يعني تكريم المحاضرين، في ملاحظة قبل كذا إنه في عندنا استبيان وزع عليكم. نتمنى من الجميع حقيقة يعني إكمال النموذج لأن بنحتاجه في معرفة توجهات فيما يخص المواصفات. جانا ردود حقيقة يعني يمكن ما شاء الله، بس الآن من خلال العدد واضح إنه في كثير ما عبوا النموذج ذا. فإذا في أحد يعني لا زال يعني المجال مفتوح النموذج للبرة ونحتاج الله يخليكم، وطبعا تكتبوا كامل المعلومات. الآن طبعا وصل معالي المحافظ الدكتور سعد القصبي إلى اجتماعنا هنا، ويحب أيضا إنه تكريم للضيوف. We are trying to okay what I said before. Okay, sorry. I mentioned general remark, by the way. I think also you need to. We distributed a questionnaire. We distributed a questionnaire about what should be, what the specification should be adopt, and what to do about them. You remember the discussion about whether to go with the rebending test, the chemical or not. So we made. I'm not sure if you have seen it or not, but I would like you to see it and also to mark it yourself.
Okay.
What is your opinion and depend as okay,
sure.
Regardless of being from ASTM. I mean, whatever you think is right. We distribute to everyone.
Yeah.
It's in
Very
Arabic
good.
and English at the same time. And we would like to know the opinion of the audience based on what they have seen from the discussion, what will be the final outcome regarding whether we to adopt ASTM 615, 706 as is, just maybe the geometrical things, change and the weight, or to add some elements of rebending and chemical analysis or to go with 706 alone to be sufficient to cover also 615, which is another option. I asked you the question about whether that could be, if there's no economical cost, so why do we need two? This could be one. So this is for the expert from the industry. I mean, if 706 could cover 615, so why do I need two? Why not just go with 706? So this is one of the options we left. Now it's time for thanking our experts, the presenter, lecturer that have participated yesterday and today, and it's His Excellency Dr. Saad Al-Qasabi, the Governor, is here with us. He's so much interested in knowing everything. I'm sure if it's not, he's so busy with so much efforts. He will be joining us here and discussing all these details. He loves them really. And you know, he was trying to be spend more time with us, but you know the obligation of the one who is in. So we would like now to invite His Excellency to and welcome our their certificate for. So we'll start, Mr. Robert Rodisky, please.
Thank you.
Pleasure to have you here. Thanks a lot. You did a great job.
Thank you.
I hope that you have enjoyed your.
Thank you very much.
Dr. Khalid Al-Hajri. المهندس أحمد محمود بهمام.
I don't know if I shall speak in English or Arabic. Okay. I will say in Arabic and then translate to English. مرة أخرى يعني أنا سعيد في الحقيقة بهالمشاركات وبحضور هذه النخبة من المتخصصين في هذا المجال. مثل ما ذكرت أمس، الحديد بالنسبة لنا سلعة استراتيجية، وهي سلعة استراتيجية للنهضة العمرانية لأي بلد. فأنا متأكد أنه هذه المشاركات أثرت الورشة، وبإذن الله تعالى نتطلع إلى مشاركات وإلى تفاعل أكبر في المستقبل، خاصة يمكن زملائنا من القطاع الخاص. نأمل أنه أثبتنا لكم في هذه الورشة فائدة التفاعل مع الهيئة وفائدة يعني المشاركة سويا في صياغة توجهات استراتيجية لبلدنا المعطاء. فأشكركم على المشاركة ونتطلع إلى مشاركات وإلى تفاعل أكثر. احنا عندنا في الحقيقة فريق عمل فني لتولي مهمة تطوير المواصفة، وحرصنا في تشكيل الفريق دائما، أو نحرص أنه يكون يمثل توازن بين القطاع الخاص والقطاع الحكومي والقطاع البحثي والعلمي، بحيث أنه المواصفة فعلا تكون مواصفة متوازنة. ويعني دائما نسعد بمشاركاتكم ومداخلاتكم. Again, thank you for coming. I'd like to thank our main speaker, Mr. Bob. Thank you for coming to the KSA, and we hope that you have enjoyed your time, although that I'm sure that you did not have enough time to, I mean, at least visit some of the sites that we have. I'd like to thank everybody who have participated in this workshop, and we look forward for continuing this kind of partnership and relationship with you. So please, continue communicating with our technical staff, and let us all together set the scene for the future standards for a very important and strategic products in the kingdom. Thank you for coming, and looking forward to see you in another event. Thank you.
Dr. Godwiski, I invite you again to the stage to proceed on. You want a break? You need 5 minutes break? Let's have 5-minute break. Okay.
good time. Yeah. Yeah. And then I go to the airport. Plenty of time. I like to be there early. Oh yeah. So, okay. Well, thank you very much. We have another something, yeah, public. Yep. No. It has to be most rebar producers are using open seam pipe. You cannot use aluminum in open seam pipe. If you're ingots? Yes, no, for the Phillips structure, for the system. Can you add it in mold as aluminum mold? You can, but that's the worst way in the world to add aluminum, and it does no value. It provides no value to nitrogen combined. It doesn't do any good for you. It doesn't tie up in the back. It doesn't do anything. It won't precipitate. It's no benefit. Because perception, people think tying up nitrogen, aluminum. And I'm saying, no, it's not going to work. Yes. Pittsburgh, yeah. Even though that's Chicago, I don't work in Chicago. I work in Pittsburgh. I work out of my house in Pittsburgh. Use the email or the cell phone number. Cell phone number is always... Yeah. Yeah. And of course, keeps changing. Everest keeps changing everything. I can give you... Well, my own stuff. So if I'm not part of Everest, which happens sometimes. Consolidated, consolidated.net, and 7 people, 7 phone numbers, of course, +1 724 444 5641. That you'll be able to get a hold of me even if Everaz is not around anymore. But there's always a real possibility. Yeah. That's what was on schedule. That's what I was shooting for, but it doesn't have so much time left, so I'll have to. But there's a couple of things I want to say. During my presentation? Oh, yeah. I still have many more slides. Oh, yeah. I can do it, yeah. Now we can do it. Regarde le
نستكمل معكم الجزء الثاني مع الخبير الأمريكي روبرت غودوسكي. Now we are going to proceed on with the American expert Robert Godwiski to proceed on, and you're kindly invited to the stage.
Okay. Something's between this and that one. I've got this, that, and that. I'm good with this. You can take those. Okay, I've got a lot more things to talk about when we have time. Try to finish up in a half hour here. And this thing is, yeah. Let's use this. Okay. Way more to talk about yet than what we have time for, but I do want to cover quickly an example of something here because it's relevant to microstructural development, and that certainly was the topic for the afternoon session. And the chemistry is very, even though it was not rebar, the chemistry is, we will see here as soon as I get this started. Is very similar. Basically, this was a light gauge structural I-beam application using this chemistry. And as you can see, it's very similar to the rebar chemistries we've been talking about. It's a 25 to 26 carbon, 125 to 130 manganese, and plain carbon steel, but with vanadium levels of 07, 08, and nitrogen contents, which aren't shown on this list, it's interestingly enough. But it was a vanadium nitrogen application. But what we're looking at here is development of microstructure as a result of the processing, section size, and chemistry. And what happened here is this application was a well-known and very popular use for vanadium nitride in North America to make what were called mini beams for the base of truck vans for virtually all the trucks you see running around the States, which are basically these boxes using the structural box, but they have, for the flooring, they needed support, high-strength supports, and they used these I-beams. They made them out of this chemistry, 80 KSI or 550 megapascal yield strength, light gauge structural products, if you will, just small I-beams, 2 to 3 inches, maybe 75 millimeters in depth. And so what happened is they complained about some problems in machining, drilling holes that were needed for fasteners, and unpredictable yield strength that was going on, and we had a complaint to go down and look at. So I went down and looked at this material, ended up getting some samples for analysis, and it's actually the 4 that you see right down here in the lowest part in red were the 4 samples of all these that we took to look at microstructurally. And so we did a microstructural analysis, and here is the chemistry of those. Here in this case I do have the nitrogen listed. So the chemistry of those 4 samples, again, 21 to 23 carbon, manganese, phos, and so on. And the properties. And as you can see, the so-called problem heats were the 347 and 967 here. And they were the problem heats. They tended to have lower yield strength, but higher tensile strength, somewhat lower elongation, but not much, but significantly different yield tensile ratios. And so we took a look at those and said, what could be causing this microstructurally? And we came up with this. This was the material that was good, that was acting the way it was supposed to. And we looked at optical micrographs, and it's pretty standard, 25 carbon ferrite pearlite microstructure, virtually the same you'd get in an as-rolled rebar of this chemistry, 25 carbon. But the material that was expressed to be a problem looked like this. And as you can see, they start to look a lot different. And basically, this was identified as a bainite, or a Wiedmann-Stoughton ferrite, really was the name of it, which is a mixture of bainite and ferrite. And that's what this structure is. Here is a comparison of them side by side. This is the good material at quarter thickness. This is the bad material. So the Wiedmann-Stoughton ferrite was definitely what was going on here. Let's go back again. Let's see. So I'll use this. If we look at the chemistry, you notice there was some hardenability difference in calculating the delta D, well, the carbon equivalent, if you will, but I don't even list that. But what we're trying to do is saying, how can we predict why 2 of the heats were bad and 2 of the heats were good? And that was the whole point then of doing the rest of the analysis. And we looked at just percent manganese and saw, okay, there is a relationship here. The higher manganese ones are the ones that had the trouble, and the variation was 1.2 to 1.4. So this kind of is an indicator of, as you increase the manganese, you have the potential in this general chemistry to run into this problem. But there was a lot of scatter in that. We looked at just carbon equivalent, a lot of scatter in that. But then I picked up this, what was called a just equation. It was in the literature. It looks like you see up here, basically a simple calculator of that came up with this delta DH, and I even forget what that stands for. But it's just a quantitative evaluation of the contribution of the hardenability elements: chrome, nickel, manganese, moly, silicon. And you put those in there, use these coefficients on them, which gives you an idea of the relative contribution of each of those elements, and then plotted that versus the yield to tensile ratio, which was the one thing that really stood out as difference from a mechanical standpoint. Since you can't really quantify the degree of Wiedmann-Stoughton ferrite, except some visual analysis, but this was easily quantifiable and very sensitive to the amount of Wiedmann-Stoughton ferrite. And so simply it says I could predict the onset of Wiedmann-Stoughton ferrite very effectively using this model. And I'm not saying this model is something you have to use. You can use any reasonably good hardenability predicting model to predict this. But it goes back to the whole thing of alloy development. When you're talking about hot rolled rods, or hot rolled rebar in this case, how do you design the alloy system? And I say it's pretty simple. You start and say you take the carbon to the maximum that's allowed, or whatever it's restricted to by usually other things like weldability or some specification or ductility. But you take the carbon, you make as much use of carbon as you can because that's the cheapest. The next thing you do in a hot rolled situation is you take the hardenability up as high as you can so that you lower the transformation temperature of the ferrite to ferrite perlite at the lowest possible temperature to get the maximum grain refinement of the ferrite and the finest perlite spacing, because those are the two major contributors to strength. In ferrite, it's the grain size. In perlite, it's the lamellar spacing. Lower transformation temperatures give you the best of that, optimizing the hardenability to get you the best you can for the cooling rate that's associated with the particular process you're running and the section size. Then you've optimized those two things, and if that's still not enough, you add the vanadium, because then that adds on top of that. And vanadium does not contribute to the hardenability to accentuate this problem. If you use niobium, it definitely would. There's a paper in the stuff I'm passing out to everybody that tells you that actually using niobium in rebar gave you this problem because of the hardenability you get from niobium. So, this whole point is that if you want to maximize your yield strength, you want to take it up as close to the start of formation of the Wiedemann-Stoughton ferrite, but not be in it. And using some model like this, if you're using an electric furnace with fairly high residuals, you can actually trim the manganese here. Say if I melt in high on chrome and nickel and moly, I can cut back on my manganese, but stay right close to that edge where I want to be for maximum hardenability without going into the Wiedemann-Stoughton ferrite. So all this kind of managing the chemistry to get the microstructure you want and need is there. Now the flip side of this, which is interesting, is and then somebody came to me recently and asked this question. People want a higher tensile yield ratio or a lower yield tensile ratio, depending how you want to look at it. You want to stay above 1.25 or below 0.8, and see we're running above 0.18 on this, which is like marginal. I wouldn't meet the ASTM spec for rebar because my yield tensile ratio is too high. What do I do to decrease it? I go to a dual phase. Guess what? They've been using dual phase now in automotive for the last 5 to 10 years with great success for this very purpose, making high strength steels but with a wide gap between the yield and tensile. That's what this does. So if we get to the point where, and I have a whole other presentation from a designer's perspective on designing material for seismic applications, maybe you want a material down here with a 0.65 yield tensile ratio instead of 0.8. Well, this is one way to get it. I'm not sure it's the right way. I'm not sure you want to do this because of other reasons, but it is one way to do it. So that's why I really wanted to point this out, is it has its good points and bad points, but it is predictable, and it is something you might be able to use in a hot rolled product. Of course, I'm not talking about QST, so quench and self-tempered applications. That's something entirely different, and you get different structures with that. And I'm sure there's balances, but I am not an expert in that area, so I'm not really going to go there. But for the hot rolled situation, this is something you should be aware of. You, generally speaking, want to stay away from it, but you actually might be able to use it in some applications. So that's one of the quick ones. That took up 15 minutes. In these handouts that I've been giving out, and I will leave here with Sasso, there is a presentation that Conrad Paulson, and he's the guy from Wisjenner and Elsner that did a lot of that, did that other major project on the yield strength determination. He did most of that work. He also wrote this, and these are recommendations that he made as a designer to CRSI, the reinforcing steel people, about what he thought was coming down the road relative to seismic requirements. So there's some interesting stuff in here. I won't really get into it in detail because we don't have the time. And for those that are able to get a hold of an electronic copy of this, it will be included in there. This, of course, is the report, and it's a very thick, the whole report is available. This is just a summary report of it. But showing us what he went to is he was talking to the rebar guys and saying, here's what we think is going to be important in our reinforcing steels. And he says, it's ductility. Strength is needed, but it's not what is important, it's the ductility. Says, where do we get it? From there. It's the only source of ductility in a reinforced concrete structure is the rebar. Nothing else is ductile. And an example of how that works with the dog bones. How does a reinforcing bar provide seismic ductility and toughness? By fully yielding and straining into the strain hardening repeatedly, tension and compression. So basically it's the tension compression test, strain controlled typically, limited 10 cycles or something like that. That's the kind of performance they're looking for. So the question is, where do you get that from the steel and what do you look for in the tensile test that says you have it? And he's saying, guess what? It's this uniform elongation or elongation at max load. So he's reaching the same conclusion that we've been talking about, whether or not it's needed in a rebar spec. But here it is, the designer guys, this has never been used in an ASTM spec, but you can probably start thinking it's going to happen. Because if these people are going to ask for it, it's going to get in there eventually. Yield strength needs to be predictable. The ratio of actual tensile strength to actual yield strength is important. And they do give some slight changes in the recommendation to the mandrel size on the bend test for the grade 80, 706. They're saying increase that. And I don't think that would be bad. I think it actually comes more in line with the ISO spec. And they're really saying take the 1.25 that's in a footnote and put it in the make it clearly a part of the specification. Reality is a lot of people don't even look at it. And I think it's more of a problem than in terms of products actually meeting it than actually happen because it's in the footnote in the current spec and people generally don't, a lot of them don't even look at it. It's not listed. You can do the calculation with the data given, but it's not always printed out. They're saying basically put it right up front. And so that's it. That was a quick report there. Yep. Yeah. Yeah. These things are not in the code yet, but they're from people that are developing the next code. So you can expect it to be coming. Yeah. Yeah. Yes. Not so important. Yeah. Good question. It sounds right, but I don't even know for sure. There's so many three-letter acronyms around, I don't remember which one is which. Yeah, it could be. I suppose it says in the report, and you should get a copy of that. And the only other thing, the thing I had as the last filler, which I have 10 minutes to give you, is my basic talk on why use vanadium nitride. Of course, this is what I go around and give to steel mills all around the world, so I do that all the time. But we sell a product called Nitrovan, which is a VCN, and it contains a fairly high level. Actually, we sell 2 grades, either 12 to 16% nitrogen, but it is basically a pure vanadium carbonitride. And we talk about why all the decisions one might have to go through as a steel producer to use this. And I kind of wrote it for rebar here, as simply saying, if I decide to if I'm in a bar mill and I want to make high strength rebar, I've got to decide how I do it. And he does have options. You have the QS&T, you have cold stretching, you have air hardenable grades, the chrome grades, and you have microalloyed steel. If you choose microalloyed, you have choices of microalloys. And I can give you a lot of reasons why I think vanadium is the best. And if you choose vanadium, I can also give you reasons why you better consider what the nitrogen level is, and you should have an appropriate or managed nitrogen level to go along with the vanadium. And as we said before, it doesn't negatively affect your strain aging, even though you may have nitrogen maxes in your spec, which is why I say be careful of nitrogen maxes in the spec, because it may hurt you. Because if this is the way you want to go, and people, believe me, people are looking at 200 ppm plus using vanadium system to get your 80 and 100 KSI as rolled rebar. Hot rolled rebar at 100 KSI, 700 megapascals with typically a 32 carbon. So you can do that with vanadium and nitrogen. And I can go to that. And of course, there's all the reasons why I use vanadium. They're all good ones. Here's the solubility curve. This is also solubility in the reheat furnace. It says why niobium doesn't work. I've said this a number of times already. Solubility, the solute drag parameters, again, the total difference between niobium and vanadium, why they're different. That can be effective, used for niobium, but not in rebar. So what I want to get to is why use a vanadium and nitrogen system. And one of the things I like to go to is this graph. And the key here, this says a couple of things about vanadium nitrogen precipitation. First thing is, it's got to be in solution in the austenite in order to be effective. In other words, precipitation that's occurring prior to the start of transformation is useless. And that's generally true for any of the precipitation strengthening mechanisms. And because of the solubility of vanadium, it's just right for precipitating during and after the actual transformation from austenite to ferrite. And the second thing is, it all happens at a fairly narrow temperature range of 500 to 700 C. In other words, immediately after transformation from the next 1 to 200 degrees is where you get your most effective precipitation strengthening. But it happens much more rapidly if nitrogen is available. If you don't have nitrogen relying on carbon, you can get strength, not as much and not as quickly. Again, here's simply saying vanadium prefers nitrogen rather than carbon. There's a very complicated way to do it. And if there's anything I want you to walk out of here, remember, and the timing is good because we're just about to walk out, remember this curve. It says if you want to get strength, it's going to be a function of your nitrogen level. So this is the increase in yield strength of material as you add vanadium. What you can expect to get, and what you say is it's a function of the vanadium content, but also the nitrogen content. And these nitrogens show a 50, 100, 150, and 200 ppm available nitrogen. It shows you what the strength contribution of the VN system is. Believe me, this is real. I've done it in multiple different alloy systems, multiple different applications, multiple different carbon levels, and you get this kind of strengthening. What I'm pointing out here with these inflections is you get the nitrogen, and this is no longer working, but I think I have another is that this slope represents vanadium nitrogen strength. The problem is that even at 200 ppm nitrogen at 0.8 vanadium, you've run out of nitrogen. Now you still get continued faster strengthening, but it starts to taper off. At 50 ppm nitrogen, by the time I add 0.25 or 0.2 or 0.25 vanadium, I've used up all available nitrogen. I can only rely on carbon. My vanadium carbide strengthening is at a lower slope, and it runs out because what's the maximum solubility carbon in ferrite? 0.02, and that's at 600 C. As it drops below that, it reduces tremendously. The point is regardless of the bulk carbon level, all the carbon below transformation goes to cementite. It's not available for precipitation. It's only the carbon in the ferrite that's available for precipitation, and it's O2 max regardless of bulk carbon level. No. Compared to what? Compared to carbon, manganese from a strength standpoint is very competitive for the strength, for a unit strength increase, but that's okay. Yeah, quenching, water is cheaper. Yeah, I can't compete with water. If you can quench it and get what you need and meet the properties, and you got the equipment to do it, you're probably going to do it. Yep. For what? Niobium? No. I don't sell niobium. Now, I don't know. Now, what the graph for niobium will start out at a steeper slope and then stop and go parallel, because niobium, you only get strength from the amount you can get in solution, and the amount you can get in solution at this carbon level is limited to something on the order of O2 or O3. If you even go to the niobium website and look at it, they've got some curves of niobium versus vanadium. And niobium is very steep at the initial contribution, and then it stops and doesn't do anything after that. So that's what niobium. So an O1 to O2 niobium addition can give you a significant increment in strength. And in fact, it can be used with this system at those low levels. But then above that, it does nothing. So that's how the niobium curve would look. Yeah. Okay, one more curve I want to show you. That's this one. So this is what I did for. This is based on data obtained from a straight rebar producer in North America, looking at making basically a 706 grade at 80 KSI and higher. Where could he go with it? And we came up with this curve based on actual data from production grades of A706 with varying amounts of vanadium and nitrogen. So this is in your handout as well. It's in KSI, sorry about that, but 100 KSI is 700 megapascals, 80 is 550, 60 is 420, so that gives you an idea of what you can do with this alloy system. And I believe alloy system was on the last session for discussion. And I just did it. So I think with that, I've covered virtually all my available material. Some of it I brushed over very quickly. And it's 3 o'clock, which is the scheduled end of this. So at this point, it's questions, if you have them. And I think by now you figured out I like to hear them. I love a challenge. Somebody can challenge me. I do say I don't know when I don't know, but I don't say that very often. Okay. And I have to say, I don't know, because I've never, and this is my first opportunity to say that, right? Only because we have not run systematic studies on the use of vanadium and nitrogen system in a quench rebar. We do have applications for quench and self-tempered structural. For example, I think it's ArcelorMittal now, it was another company, makes these, and Grand Range in Luxembourg makes these large section structurals, the I-beam structural grades, and they do quench and self-temper. Same thing you're doing with rebar, although the self-temper temperature is a lot higher for better ductility and toughness. Their self-temperature, their minimum is about 600, which is ideal for precipitating. They're using the vanadium nitrogen system to build up the strength of the ferrite perlite core. And it's ideal because the thermal process is ideal for maximizing the strength of the ferrite perlite with vanadium nitride while they're getting the martensite outside edge shell for the additional strength. So it's a very effective for that. In other words, so the question is, can we do a similar thing with rebar? You know, where can we go? Where can we take, and certainly with rebar, if you got the system and you're using water, you're going to use that. But there's a limit to how far you can go, right, in terms of maybe ductility issues. You know, you can only quench it so deep and then it's not going to be ductile anymore, those sorts of things. So you still want to optimize all that, but after you've optimized that, now go with the vanadium nitrogen system, and there's a lot of indication out there in similar but different applications that says vanadium can get you the next bump, and virtually in the same quantitative level as what you're seeing here. But that's yet to be tested because there hasn't been a demand for it. So what you've got to do is get to a point where, gee, I'm making a good product with my QNST process, but I need to go to the next level on strength. Can I do that with vanadium? Presumably, you'll be able to sell it. Now, people aren't caring right now when they make this 100 KSI grade, they're using huge amounts of vanadium. But they don't care because they're competing against this 1035 grade, which is 9% chrome. Oh, I can compete with that. So it's not a problem yet. But somebody else makes it at half the vanadium content, then they're going to have a problem. So eventually it will be. Eventually economics will win out. But we have to continue to optimize that. So I think vanadium can help. Is it economically viable? It depends on a number of situations. There you are. Been doing this for 15 years, have been asked that question for 15 years. I say this, precipitation strengthening reduces ductility, regardless of how you get it, in a fairly measurable and predictable way, but it doesn't fall off the cliff. You know, it just decreases, the strength goes up, ductility goes down. Toughness, in many, there's a paper we're publishing at the Mike Krasinski Symposium at MS&T next month that we did on some plate up at Regina, and toughness was just as good with the vanadium-bearing bainite grade as it was without. So there was no toughness loss whatsoever. You can expect a little bit from precipitation strengthening of ferrite perlite, but it's predictable, and typically you compensate for that with a better grain refining process. In other words, end up with a finer grain size, you compensate for the toughness loss. So at the end of the day, most of the so-called ductility loss by adding vanadium and or the vanadium nitrogen is strictly, I'm raising the strength, therefore I get a predictable ductility loss. It's not because of the presence of that, it's because the strength has gone up. So you get that regardless of your strengthening mechanism, not because it's vanadium or because it's vanadium and nitrogen. So keep that in mind as you look at it. Yeah, there's going to be an interrelationship of those two, but it is not a fall off the cliff kind of issue. Suddenly everything goes bad. It's very predictable. And it's all related to the strength. Well, it's interesting you say that because we've been producing that product for 20 to 30 years in North America, and I've never known anybody to use niobium. They all use vanadium. Chromium. Okay. I heard niobium, not chromium. I'm sorry. Okay, well, you can do chrome, but keep in mind, this goes back to what I said previously. Adding chrome is for a different reason than adding vanadium. In other words, just like I said for the rebar, we will say for 1080, because that's why I learned it. This is in 1080 high carbon rod for pre-stressed strand. You first add the carbon up to the maximum you can. In that case, you're limited by grain boundary carbides in the center due to segregation and whatever your segregation control capability is and your wire drawing capability. You have to minimize potential for cuppy breaks during wire drawing. You do that by minimizing grain boundary carbides. You take your carbon up to the level where you start to get that, you back off, that's as high as you're going to go. The next thing you do is you minimize the perlite spacing. In other words, get the finest possible perlite spacing you can get with the process that you have, with the given cooling rate that you have on your process, because you've got to use it. And that's what that means, is adjust the hardenability so that you maximize the cooling rate to get the finest possible perlite with the process you have. And you know you've gone too far when you start to get degenerate perlite or discontinuous perlite lamellae. You've gone too far because you can't draw that. That defines a limit. Once you've done those two things, there's nothing else to do but add vanadium. So the chrome helps you with the hardenability, and you should optimize your hardenability. But you use some combination of manganese, chrome, but there is a limit on how much hardenability you can add. You can use any of those elements. One doesn't necessarily replace the other, they're just additive. Okay? Chrome may do a better job of refining perlite spacing than manganese. Maybe silicon will. There's some high silicon grades being made, going to 80 silicon in these content. And silicon has been known to actually improve. So all that is good. But you do that independent of the vanadium addition. You do that first. You get your optimum structure and strength. Then, if you need more, you go to the vanadium. That's how you approach that whole alloy concept. That's how you should approach any alloying concept with rebar, whether you're using the quench and temper system or using a hot rolled system. The concept's the same. Optimize what you're using relative to carbon level, to hardenability, to match the cooling rates you've got in your process. Then you can add vanadium because it's always incremental on any of those systems. And it doesn't contribute to hardenability. It has, one of the reasons I say to use vanadium, it has the least number of negative side effects of any of the alloy systems you can use. You add it and you forget about it, and it works. Chromium in what application? You asked about the. Okay, what kind of steel are you talking about? Plates, bars, hot rolled bars, hot rolled plates, control rolled plates. The answer varies depending on where. Okay, I'll pick some examples. Niobium and vanadium can work together, but the reality is if you use niobium correctly and effectively, the presence of vanadium is probably not needed. A lot of line pipe today is made with a niobium-vanadium system, but much of it doesn't need the vanadium. It's there as a crutch in case they don't use the niobium correctly. And the whole reason is niobium works better if you don't add nitrogen. Vanadium works better if you do. And so if you're using niobium, what niobium gives you to give its toughness is it gives you It raises the recrystallization stop temperature, so you get pancaking of the austenite grain during the rolling process. Now, that does not refine the grain as everybody wants you to think, but it just changes the shape. But if you've ever taken a balloon full of water and it's nice and round, but you squash it down, the volume of the water doesn't change, but the area of the balloon increases dramatically. That's what you're doing with the austenite grain. And when it comes to toughness, the best way to stop the propagation of a brittle crack is to hit a prior austenite grain boundary. And so the whole reason why niobium works so effectively in those applications with the pancake rolling below the recrystallization stop temperature is because you get this huge increase in the surface area of the prior austenite grain boundary. And that gives you the toughness. But if you do that, you got to roll at low temperature. You can't tie it up with nitrogen, so you got to have low nitrogen. But if you do all that, it works very effectively, but it does not maximize the vanadium benefit. You get something, but not nearly at the rate that you expect to get with a vanadium nitrogen system. And so eventually people learn how to live without it. So the really good pipe guys don't use it at all. But then when you get into the bainite grades, there's a whole nother level again where it seems like vanadium could be useful. But that gets really out there right now. We don't even know how to explain all that. So there is some synergy. It can be synergy, but unfortunately because of the plus nitrogen, negative nitrogen effect, it's difficult to really make maximum use of. If you're doing it in rebar, you're going to have high nitrogen. You're going to put vanadium in there. You hope to get a little kick, that first kick from a small amount of niobium addition from its austenite conditioning, and then the rest of it, you get strength from precipitation strengthening. Maybe that works, but still the sum of strengthening is not necessarily the sum of what each individual one would give you. In other words, the total strength you get from adding them together is never going to be as much as the individual strengths of each one added together. That's the way it is. But you can still make a good product that way. Now, your second question. Yeah. You're adding the niobium to the steel or rolling, not to the rolls? Okay. Yeah. I'm going to have to say, I don't know. Yeah. All of those questions I don't know the answer to, so I can't really even begin to address it. Yeah. Chrome and vanadium are doing things very differently in the steel, and so to say you can replace one with the other certainly is not true from what the metallurgical response is going to be. Whether you get similar mechanical responses or not is probably just circumstantial. And I don't know the circumstances well enough to even venture a guess. That's a very unique and specific problem that would need to be addressed, and I can't answer that off the top of my head. That's one I will have to say I do not know. I think we're getting cut off here.
At the end of the workshop, we cannot but thank the American expert, Robert Godwiski, for his presentation, and the other speakers, Dr. Khalid Al-Hajri, مهندس أحمد همام, Engineer أحمد همام, وتتقدم الهيئة السعودية للمواصفات والمقاييس والجودة بخالص الشكر والتقدير على حضوركم وتفاعلكم معنا هذا اليوم، والشكر الموصول للمحاضرين الذين بذلوا جهودا في إعداد أوراق العمل. شكرا لكم جميعا، ونلتقيكم بإذن الله في مناسبات أخرى، والسلام عليكم ورحمة الله وبركاته.
Thank you everybody for your good questions and interaction. I was afraid that wasn't going to happen, but it was been very good. And as you can see, that's what gets me going. Thank you, thank you, thank you. Very good. No, I think somebody came and got it. We went without it.
لا لا أخذوه.
Yeah. Yeah.